Welcome to the Explainer. Today, we're diving deep into Chapter 19 of the completely legendary Feynman Lectures on Physics. We're going to be exploring the profound physical realities behind how complex objects balance, how they move, and how they spin. I mean, have you ever actually wondered why a spinning ice skater suddenly speeds up when they pull their arms in? Or why just walking outward on a merry-go-round feels so bizarrely difficult? Well, it all comes down to the fundamental rules we're going to unpack right now. So here's our game plan for today. We'll start with the center of mass, move on to locating the balance point, figure out how to find the moment of inertia, discuss energy and rotating systems, and finally, tackle the strange Coriolis force. We are kicking things off with a pretty massive philosophical idea from the text. Newton's laws have this amazing, almost magical self-reproducing property. Think about a baseball. It's actually a tremendously complex system made up of billions and billions of interacting atoms, right? But because Newton's laws reproduce themselves on a macro scale, we can treat that incredibly complex body as if all of its mass were perfectly concentrated at one single point. And finding that point is exactly what makes calculating motion possible, without, completely losing our minds. Part 1, the center of mass. By definition, the center of mass is literally just the average position of all the parts of a system weighted according to their individual masses. It's the exact spot where the net external forces act on an object. And what's really fascinating here is that this point doesn't even have to be located inside the physical material of the object itself. Just picture a hula hoop or a donut. The center of mass is floating right there in the empty metal. It's a totally abstract mathematical point, yet the entire object dynamically behaves as if all its weight is sitting right exactly there. So, what if you have a weird L-shaped object? Well, you don't actually need to do complex math on the whole thing at once. You can just break it down into two simpler geometric pieces. Let's call them A and B. You find the center of mass for piece A and the center for piece B. Then you just treat each piece as a single point mass. If you draw a straight line between those 2 points, the total center of mass for the entire compound body is guaranteed to lie right on that line. It's a brilliant little trick that saves you from starting from scratch every single time. Moving on to part 2, locating the balance point. Now, if you've ever taken calculus, you know you can use integrals to find these balance points. But what if we want to avoid pages of tedious equations? How do we find that exact balance point in complex, continuous shapes without getting entirely bogged down in the math? Well, the text reveals a wildly brilliant geometric trick that lets us shift away from abstract calculus and rely on intuitive spatial reasoning instead. This trick is famously known as the theorem of Pappus. Suppose we want to find the center of mass of a perfectly flat right triangle. Instead of doing flat 2D math, imagine taking that triangle and sweeping it through a full 360-degree rotation around its vertical axis. By sweeping it through space like that, you generate a 3D solid, specifically a cone. So here is exactly how the theorem works. You take a plane area, like our triangle, you sweep it through space. The theorem states that the total volume of that newly generated 3D shape exactly equals the original 2D area multiplied by the distance its center of mass traveled during the sweep. And because we already know the standard formula for the volume of a cone, we can just effortlessly work backward. We can calculate that the center of mass sits exactly 1/3 of the way along the base of the triangle. Honestly, it's a beautiful geometric shortcut to just completely bypass heavy calculus. Let's dive into part 3, finding the moment of inertia. Okay, just as mass resists linear movement, think about how tough it is to push a stalled heavy car, there is a rotational equivalent. It's called the moment of inertia. This is simply an object's physical resistance to spinning. But here's the catch. It doesn't just depend on how heavy the object is. It's calculated by summing the masses multiplied by the square of their distance from the axis of rotation. The further the mass is from that pivot point, the exponentially harder it is to spin. Spinning a rod from the very end requires you to move a lot of mass that is sitting very far away from your hand. In fact, if you try to swing a rod from its end, the mathematical factor of its resistance is 1/3. But if you hold it perfectly in the middle, right at its center of mass, and twirl it like a baton, that factor drops all the way down to 1/12. That means it is fundamentally exactly 4 times easier to spin a rod from its center than to swing it around from its end. In the world of rotation, distance from the axis dictates absolutely everything. And thanks to something called the parallel axis theorem, we can build a practical reference sheet of standard shapes. If we know the moment of inertia for an object spinning on its center of mass, we can easily calculate the resistance for literally any other parallel axis just by adding the mass times the distance squared. It's fantastic because we don't have to reinvent the wheel or reintegrate the calculus every single time we decide to move the pivot point.
Part 4. Energy in rotating systems.
If you remember your basic physics, linear kinetic energy is 1/2 times mass times velocity squared. Well, the energy of a spinning object mirrors that perfectly. We just swap out the linear variables for the rotational cousins. We replace mass with I, our moment of inertia, and we replace linear velocity with angular velocity, which is represented by the Greek letter omega. So your rotational kinetic energy is simply 1/2 I omega squared. Simple, elegant, and totally analogous to what we already know. But here is where things get wild. Think back to that ice skater spinning on the ice. When they pull their arms inward, their mass gets closer to the axis. That means their moment of inertia decreases. Now, to conserve total angular momentum, their spin rate, their angular velocity, must suddenly increase. They spin way faster. But if you actually sit down and run the math, the overall rotational kinetic energy of the skater actually goes up. So where did this extra energy come from? Well, it wasn't magic. The skater actually had to use physical muscle energy to pull their arms in against the outward pull of centrifugal force. Doing that physical work injected extra kinetic energy directly into the spinning system.
And finally, Part 5. The strange Coriolis force.
Let me pose a question that almost sounds like a riddle. Why does moving in a perfectly straight line outward on a spinning carousel require you to physically push sideways? The text sets up a brilliant thought experiment for this. Imagine a guy named Mo walking radially outward from the exact center of a merry-go-round, while his friend Joe just watches him from the stationary ground outside. From Mo's perspective on the actual ride, he's just walking straight out from the center. But from Joe's stationary perspective looking down at him, Mo is actually moving in a sweeping, curved path. And physics strictly tells us that for an object to curve like that in absolute space, some invisible force simply must be acting on it to accelerate it sideways. So, Mo is actually experiencing a whole cocktail of forces. If you write out the math from the perspective of someone living right there on that spinning ride, the centripetal force breaks down into 3 distinct pieces. But without a doubt, the strangest piece is the Coriolis force. It's an apparent force that pushes exactly at right angles to your velocity, meaning if you walk forward, it pushes you sideways. It is the necessary force you must physically exert to increase your angular momentum as you get further and further away from the center. The mathematical magnitude of this weird sideways push boils down to this perfectly balanced expression, 2m omega v. That's 2 times the mass times the rotation rate times your velocity. This elegant little equation calculates that strange Coriolis force, proving mathematically that simply moving in a straight line within a rotating system requires us to fight against real, invisible, sideways pressures. And that really brings it all home to you and me. Because, we're all living on a massive spinning carousel right now called Earth. As you walk around today, you are subject to these exact same invisible forces. Your body is constantly navigating the center of mass, the moment of inertia, and yes, absolutely even the Coriolis force, simply by existing on a spinning planet. So, what hidden inertial forces are acting on your body right now? I hope this explainer leaves you eager to look at the everyday world around you and uncover more of the incredible physics hiding right there in plain sight.
Welcome to today's explainer. We're going to be exploring one of nature's most deeply hidden and honestly most elegant mathematical blueprints. It's a concept that shows up literally everywhere you look, from the massive scale of outer space all the way down to the tiny, microscopic world of quantum mechanics. It's called the harmonic oscillator.
So, to get us started, I want you to think about this. What do a swinging pendulum, the vibrations of electrons inside an atom, and the flow of charge in an electrical circuit actually have in common? I mean, on the surface, these are vastly different physical setups, right? One is mechanical, one is quantum, and, well, one is electrical. But, nature has this incredibly surprising trick up her sleeve.
The answer is that they all follow the exact same equation. It's this delicate balance where the force pushing them back to the center is perfectly proportional to how far they've strayed. The mathematical rules governing a heavy grandfather clock are the exact same rules governing the light waves generated by an atom, or even just a thermostat trying to fix a room's temperature. It's actually fascinating how the universe constantly reuses its absolute best ideas.
Okay, so here's our roadmap for today. We'll start with the universal physics equation, look at a mass on a spring, uncover a secret circular connection, talk about initial conditions in energy, and finally wrap up with forced oscillations and resonance.
Let's jump right into part 1, the universal physics equation. You know, studying one thing in physics often hands you the cheat code for understanding something completely different, like how understanding acoustics basically laid the groundwork for optics. And it all comes down to what's called a linear differential equation with constant coefficients. Okay, I know, that sounds incredibly dense, but don't let the math jargon scare you off. The physical meaning is actually beautifully simple. It just means the time pattern of the motion remains exactly the same no matter how strong the initial push is. The underlying rhythm just doesn't change with its intensity.
Moving right along to part 2, a mass on a spring. Okay, let's dive into this and make that abstract math a bit more real. Just picture the simplest mechanical system you can think of. A mass, we'll call it m, hanging on a perfectly linear spring. First, the spring stretches just enough to balance out gravity. That's its happy place, its equilibrium position, which we'll label 0. Now, if we pull the mass down by a distance x, the spring gets stretched and exerts a restoring force that pulls back up. And because the spring is linear, that pulling force, and therefore the mass's acceleration, is precisely proportional to the negative of its displacement. It always wants to return home.
Let's break down the mechanics here. The restoring force is pulling back exactly in proportion to how far you stretch it. Now, the heavier the mass, the more inertia it has, right? That means it takes longer for those forces to actually get the mass moving, which stretches out the time of a full cycle, what we call the period. On the flip side, a stiffer spring snaps back more quickly, which increases its natural frequency. But here is the absolutely mind-blowing part. The period does not depend on how far you pull it down. Think about it. If you pull it twice as far, it has twice the distance to cover. But the spring is also pulling back twice as hard, so it ends up taking the exact same amount of time to get back to the start.
Which brings us to part 3, the secret circular connection. Now this is where things get really wild, because we're going to connect our bouncing spring to something that seems totally unrelated, spinning in a circle. Imagine a particle moving smoothly in a perfect circle at a constant speed. There's no spring here. It's just tracing a radius, r, around a center point, with an acceleration pointing inward to keep it on that circular path. At first glance, you'd think this has absolutely nothing to do with our bouncing mass, but the mathematics? It tells a totally different story.
Imagine tracking that particle on the circle, but, and this is key, completely ignoring its up and down vertical movement. Imagine shining a bright spotlight straight down from the top and tracking only the horizontal shadow, the X projection, as it moves back and forth along the axis. Here is the magic. If you calculate the horizontal acceleration of that shadow, it's directly proportional to its distance from the center. It exactly matches the equation of our spring.
And this brilliantly illustrates the whole concept in a real-world experiment. Imagine a light projecting from the left. In the middle, you've got a crank pin moving in a circle, and right next to it, a mass bouncing up and down on a spring. The light casts shadows of both of those objects onto a screen on the right. If you perfectly match the angular speed of the spinning wheel, what physicists call omega 0, to the natural frequency of the spring, those two shadows track perfectly. They just move up and down together in absolute precise harmony. Uniform circular motion and a bouncing spring are mathematically identical.
All right, on to part 4, initial conditions and energy.
So the equation gives us the rhythm, right? But it doesn't tell us the size of the bounce. That all comes down to energy. Think of the energy in this system as this beautiful, continuous, perfectly balanced dance. You have potential energy, the energy stored up in the stretch of the spring. It's at its absolute maximum when you pull the mass all the way down, but it drops to 0 exactly as it passes that resting middle point. And then kinetic energy, the energy of actual motion, does the exact opposite. It's 0 at the very bottom when the mass briefly stops to change direction, but it hits its maximum speed right as it flies through that middle equilibrium point. The total energy stays perfectly constant. It's just passing smoothly back and forth between potential and kinetic.
So I want to highlight this number right here, 4. Why 4? Because the total energy in our oscillator depends on the square of the amplitude. And amplitude is just how far you initially pull it. So if you pull the spring down twice as far, you don't just double the energy. 2 squared is 4. You actually get an oscillation with 4 times the energy.
And finally, part 5, forced oscillations and resonance.
Okay, so up until now, we've just been pulling the spring and letting it go. But what happens if you force an oscillator to move by continuously pushing it? Well, it has a two-part reaction. First, you get the transient response, which is this messy, chaotic initial reaction as the spring basically tries to figure out what you're doing to it. But that dies out. Then, what takes over is the steady-state response, where the mass locks perfectly into step with your pushing force. If you push very slowly, at a low frequency, the mass just moves in the exact same direction as your hand. But if you try to shake it back and forth super fast, a high frequency, the mass can't keep up because of its inertia, and it actually pushes back negatively against your force.
The legendary physicist Richard Feynman actually hit the nail on the head with this. He grounded this complex idea into a universal experience we can all relate to: pushing a child on a swing. If you just push at random speeds, nothing really happens. You end up pushing when you should be pulling. But if you adjust the timing of your pushes to perfectly match the swing's natural frequency, boom, you get an enormous displacement. The child goes incredibly high.
So, what does this all mean? Well, it leaves us with this totally wild final thought. According to the pure math of the linear differential equation, if your pushing frequency exactly matches the natural frequency of the object, the amplitude should approach infinity. Literally, it should bounce higher and higher forever. But obviously, we don't see infinite bouncing in the real world, right? Friction and structural limits get in the way. So the math promises infinity, but reality steps in. And it forces us to ask, when mathematical resonance goes to infinity, what breaks first? Does the spring snap? I'll leave you to ponder that real-world limit. Thank you so much for exploring the universal blueprint of the harmonic oscillator with me today.
Welcome to this explainer. Today, we're diving deep into the physical meaning of Chapter 25, exploring one of the absolute most foundational tricks in all of physics. We're going to look at how the mathematics of linear systems applies to pretty much everything around us. I mean, we're talking about everything from how you tune a radio to your favorite station, all the way to how automotive engineers design a perfectly smooth car suspension. It's this incredible journey from really abstract math to tangible, everyday physical reality. Let's get into it.
So, before we get bogged down in any heavy differential equations, we really need to start with a big question. If you look at the work of physicists and engineers, you'll find they spend, maybe 50% of their time relying entirely on linear systems. But let's be real. The universe is incredibly messy, right? Things break, they stretch totally out of proportion, they crash into each other. So why on earth are these straight-line, perfectly linear equations the absolute bedrock of how we understand the physical world?
Well, the truth comes straight from the legendary Richard Feynman himself, and it's brilliantly pragmatic. He said, the answer is simple, because we can solve them. It's so true. While reality is often chaotic and completely nonlinear, we lean heavily on linear equations because they actually allow us to find concrete mathematical solutions. When displacements are small, say a pendulum just gently swinging, or a spring being pulled just a tiny bit, nature actually closely approximates a perfectly linear system. And if we can understand these linear rules, we basically unlock the ability to understand a massive chunk of the universe.
Okay, here's our quick roadmap for today. First, the magic of linear systems, followed by superposition and radio tuning. Then we'll cover the role of friction, physical analogs, and finally, circuit impedances.
Section 1. The magic of linear systems. The math behind the reality. The defining mathematical feature of a linear system is remarkably elegant. Basically, if you have an operation on two variables added together, let's just call them x and y, the result is the exact same as if you performed the operation on x independently and then just added it to the operation on y independently. In short, you can take a massively complicated problem, break it into tiny, manageable pieces, solve every single one of those simple pieces on its own, and then just add the solutions together to get your final answer. It is literally a physicist's ultimate cheat code.
Section 2. The principle of superposition. Adding the pieces.
Now, how does this mathematical idea of addition actually translate to physical reality? Imagine a really complicated wavy force acting on a system. We can mathematically split that thick, messy force into two much simpler sine waves. Let's call them force A and force B. Because the system is linear, the physical response works exactly the same way. We just calculate the simple response to force A, which gives us motion A. We calculate the simple response to force B, giving us motion B. Then we literally just add them together and boom, we get our final combined motion. The total response is simply the sum of its individual parts.
And get this exact same principle scales seamlessly into electricity. If you have a blob of charge, let's label it Q sub A, it creates an electric field at a certain point, which we'll call E sub A. If you bring in a totally different charge, QB, it creates its own field, EB. Do they interfere and create some unsolvable mathematical mess? Not at all. The total electric field is just the simple vector sum of EA and EB. The great laws of electricity, Maxwell's equations, are linear, which means this insanely powerful rule of superposition applies perfectly.
Taking this a step further, think about a truly continuous, erratic force, one that's rising and falling completely unevenly over time. Instead of trying to solve for that whole complicated, messy curve all at once, we can imagine slicing it up into a succession of quick, sharp hammer blows, or impulses. First an impulse, then another, and another, just all packed tightly together.
This brings us to a wildly powerful technique called the Green's function method. Here is the logic. A single hammer blow usually results in a very simple damped oscillation. By treating a complicated continuous force as a rapid-fire series of those tiny hammer blows, we can use the mathematical process of integration to simply add up all those individual damped oscillations. If you know how a system reacts to just one tiny impulse, you possess the mathematical key to solve for literally any arbitrary continuous force in the universe. You just add up the pieces.
Section 3. Resonance and radio tuning, separating the signals.
Think about what's happening at your car radio antenna right now. It is being absolutely bombarded by the electric fields of every single radio station in your entire city simultaneously. By the principle of superposition, your antenna is reacting to all of them at once. It seems like it would be impossible to disentangle them. But when you tune your radio, you are adjusting a resonance circuit. For the specific frequency you actually want to hear, let's call it omega A, the circuit creates this massive, impossibly sharp spike in response.
So imagine two stations broadcasting with the exact same power. Station A is on your tuned frequency, and Station B is on a completely different one. The physical response to your tuned frequency is absolutely tremendous. It rides that sharp resonance peak all the way up. Meanwhile, the response to the competing frequency is just tiny and flat. So even if the two signals hit the antenna with the exact same strength, the tuned frequency completely drowns out the competing one. We've used resonance to cherry-pick exactly what we want to hear out of a giant sea of superposition.
Section 4. The role of friction, rounding off the peak.
Now, up until now, we've kind of been talking as if these systems just oscillate perfectly forever. In a magical, friction-free universe, if you pushed an oscillator at its exact natural frequency, the amplitude would build and build and build, shooting to infinity until the system literally ripped itself apart. But physical friction acts as a vital dampener. It bleeds off a little bit of energy during every single cycle. Friction rounds off that dangerous peak. The more friction you have, the lower and flatter that resonance curve becomes, which is exactly what keeps our physical systems from tearing themselves to shreds.
Section 5. Mechanical and electrical analogs. The grand analogy.
Okay, here's a massive, almost magical secret of the universe. Entirely different physical systems actually operate using the exact same mathematics. Take a mechanical mass bouncing on a spring with some friction and compare it to an electrical inductor, resistor, and capacitor in a circuit. The equations governing them are completely identical. Mechanical mass, the inertia that keeps something moving, is mathematically identical to electrical inductance, which keeps current flowing. Friction matches up perfectly with electrical resistance. Spring stiffness maps to inverse capacitance, and mechanical force maps perfectly to electrical voltage.
Because the math is identical, engineers can perform what honestly feels like magic. Suppose you're designing a car suspension, and you want to know how it handles a super bumpy road. Instead of building an expensive, complicated physical car, swapping out heavy metal springs, and physically driving it over actual bumps, you just build an analog computer. You create a simple electrical circuit right on your desk. You use an inductor to represent the heavy wheel, a capacitor for the spring, and a voltage generator to simulate the bumpy road. If your fake car bounces too much, you don't need a wrench, you simply turn a little dial to increase the electrical resistance, which instantly tests stronger shock absorbers. The math doesn't care if it's counting heavy metal springs or invisible electrons. The answers are exactly the same.
Section 6. Series and parallel impedances, combining the elements. When we combine circuit elements, like those inductors, resistors, or capacitors, they create what's called a total impedance. Impedance is basically just how much the entire block resists the flow of alternating current. And we calculate this differently based on the physical layout. If they are lined up end to end, what we call in series, the exact same current flows through both, and we simply add their individual impedances together. If they are split side by side, in parallel, the current actually divides between them, and we have to add their inverses to find the total effective impedance of the system.
To simplify even the most complicated, tangled webs of electrical circuits, we rely on two elegantly simple rules known as Kirchhoff's laws. First, current can't just magically appear or disappear. At any junction in the wire, whatever current flows in must exactly equal the current flowing out. Second, energy is perfectly conserved. If you track a charge around any closed loop in the circuit and bring it right back to where it started, the net work done, so the total changes in voltage will always sum to zero. These basic rules, which are built entirely on the solid foundation of linear systems, allow us to untangle and analyze pretty much any circuit we can dream up.
So, we've spent our time today seeing how immensely powerful linear systems really are. We can break them apart, solve the easy pieces, add them back together, and even use electricity to perfectly mimic mechanics. And we do this because, as Feynman noted, we can actually solve these equations. But it leaves us with a totally fascinating final thought to ponder. What happens when you pull a spring too hard and it actually snaps? Or when you push a pendulum until it swings wildly over the top? The linear math completely falls apart. So how do physicists tackle the beautiful, unpredictable chaos of the universe when things break, warp, and finally stop acting in a straight line? That is where the real challenge begins. Thank you so much for joining me on this explainer. I'll catch you next time.
All right, let's just dive right into this explainer. We're going to unravel the fascinating and honestly kind of mind-bending physical reality behind how light actually travels. We interact with light every single waking second, yet the true mechanics of how it gets from point A to point B are way stranger than fiction. Because think about it, how does light actually know which path is the fastest? It's a question that completely puzzled scientists for centuries. I mean, when light travels, it doesn't just blunder forward, it somehow seems to make calculations. To figure out how it does this, we're going to need to strip away our everyday illusions about the physical world. So here's our roadmap to crack this mystery. We'll start with the basics of light, move into reflection and refraction, tackle the principle of least time, look at some optical illusions and lenses, and finally answer that big question, how does light know? Part 1. The basics of light. We're going to start by looking at light through a very zoomed-out lens, because before we can understand the quantum truth, we have to look at the classical models that scientists relied on for hundreds of years. So the key thing to grasp here is that we're starting with what physicists call geometrical optics. Basically, it's a rough approximation. It treats light as these simple, straight rays. And yeah, it's super useful for building everyday stuff like glasses or cameras, but spoiler alert, it's a model we're going to have to completely unlearn by the end of this explainer. Moving on to part 2, reflection and refraction. Let's talk about the basic rules humanity stumbled upon just by watching light hit everyday things. These are the phenomenon you experience every time you look in a bathroom mirror or stare into a swimming pool. You see this simple rule in action all the time. It's been known since antiquity. The angle of incidence equals the angle of reflection. Light bounces off a mirror at the exact same angle it comes in at. It literally behaves just like a billiard ball bouncing off a cushion. But you know, what happens when light hits water? It doesn't just go straight, it breaks or refracts. Whenever light passes from a less dense medium, like the air around us, into a denser one, like a pool of water, its path takes this sudden, sharp turn. Now this is where it gets really cool. Just compare the measurements Claudius Ptolemy took way back in 140 AD to the exact mathematical law discovered almost 1,500 years later. Ptolemy's numbers were incredibly close. He meticulously tracked these angles just by observing. But it wasn't until 1621 that Willibrord Snell finally cracked the actual mathematical formula, Snell's law, that connects these angles using sines. Think about that. Humanity had the raw data for a millennium and a half before figuring out the hidden math. Which brings us to part 3, the principle of least time. Because having a mathematical formula is great, but to really do physics, like the deep dive found in chapter I-26 of the Feynman lectures, we need to understand the profound why behind those numbers. Why does light bend exactly that much? Well, in 1650, Pierre de Fermat came up with this incredibly elegant idea, and it changed absolutely everything. He realized that light isn't just blindly taking the shortest physical distance. Instead, it's actively optimizing for the shortest time. This is Fermat's famous principle of least time. To really wrap your head around this, picture a lifeguard trying to save a drowning girl. If you're the lifeguard on the beach and she's out in the water, running in a perfectly straight diagonal line isn't actually the fastest way to get to her. Why? Because you can run way faster on the sand than you can swim in the water. So what do? You naturally run farther down the fast sandy beach, so you spend way less time slogging through the slow water. You calculate this optimal bent path. Well, light does the exact same thing. It travels slower in water than it does in air, so it literally bends its path to maximize its time in the fast air. If we actually map out the total travel time of all the possible paths light could take, we get a curve, and light naturally finds the exact bottom of that curve. But here is the absolute crucial detail. At the very bottom of this curve, any slight shift to a nearby path takes practically the exact same amount of time. Lock that idea away in your brain because it is the secret key to unlocking the quantum reality we're going to get to in a minute. All right, part 4, optical illusions and lenses. Let's see how this principle actually plays out in the real world and in the optical engineering we use every single day. This is Fermat's principle happening right before our eyes in nature. Because light travels faster in thinner, hotter air, it naturally bends to save time. So on one hand, the Earth's atmosphere actually bends the sun's rays over the horizon, meaning we literally see the sun after it has technically already set. No way, right? And on the other hand, that classic mirage on a hot highway, that isn't water. That's light from the sky dipping down into the hot, fast-moving air right above the asphalt and then curving back up to your eye to save time. You are literally hallucinating puddles of sky. Now, what if we want to harness this? Say you want to build a perfect optical device that takes light spreading out from one point and focuses it all perfectly back to a single new point. You run into a major hurdle. Light only wants to take the path of least time. So to trick it into taking multiple paths to focus together, you have to perfectly engineer your device so that every single possible path through it takes the exact same amount of time. And that is exactly what a converging glass lens does. See, glass slows light down. So by making the lens thicker in the middle, it heavily delays the light that's taking that short, straight shot right through the center. This perfectly compensates for the travel time, allowing the light taking the longer outer paths, which get to spend more time zipping through the fast air, to catch up. And boom, every single ray arrives at the focal point at the exact same moment. This exact same principle of least time is what dictates the swooping, parabolic shape of massive telescope mirrors. The shape is so perfectly calculated that whether a distant star's light hits dead center or way out on the very edge of the mirror, the total distance, and therefore the total time it takes to bounce to the focal point is identical. That incredible bit of physics is exactly what allows humanity to gather the impossibly faint light of distant galaxies. Okay, part 5, how does light know? We've reached the climax of this explainer. We know light takes the path of least time, but it's finally time to peel back the last layer of the onion and reveal the strange underlying quantum reality. Legendary physicist Richard Feynman really hit the nail on the head when he asked, does light smell the nearby paths? Does it check them against each other? And the mind-blowing answer is yes, it actually does in a way. We have to completely throw out the classical idea of light just bouncing blindly off surfaces like billiard balls. We have to embrace this bizarre truth that light actively feels out its options. It's not an accident that it finds the fastest route. And the crazy part is, we can actually prove this. If you force waves through a wide opening, they travel straight to their target because they have the space to check the nearby paths and find that fastest route. But if you squeeze them through a tiny, narrow slit, so narrow that you physically block them from checking those adjacent paths, they basically freak out. They fan out in all directions in total confusion, completely abandoning the straight line. The physical meaning here, which chapter I-26 unpacks so beautifully, is just absolute quantum weirdness. Light is not a single ray shooting through space. It's an accumulation of photons. And a single photon takes literally every available path from point A to point B, all at the exact same time. Every single path is represented by a rotating vector, kind of like a tiny little clock hand spinning around as the photon travels. When we add all those tiny clock hands together, we get this incredibly beautiful, chaotic knot of probability. And here is where the magic happens. Remember the bottom of that curve we talked about earlier? For the paths taking the absolute shortest time, those clock hands stop spinning relative to each other. They line up, pointing in the same direction, and build up into a massive probability vector.
Meanwhile, the clock hands for all those long, crazy, zigzagging paths are spinning wildly. They point in every random direction and completely cancel each other out. So light doesn't really choose the fastest path. The fastest paths add up, while all the other paths literally destroy each other quantum mechanically.
And that right there is the true breathtaking reality of optics. Honestly, it leaves you wondering if this simple, everyday reflection you see in your bathroom mirror is actually the result of a chaotic, universe-spanning quantum calculation where light takes every path simultaneously. What else about our everyday reality is just a convenient, classical illusion? Keep questioning what you see. You know, it's kind of wild to think about, but how exactly do we steer invisible waves across the globe to a highly specific location without ever physically moving the antenna? It literally sounds like magic, right? But it's actually this massive, high-stakes engineering puzzle built entirely on the beautiful quirks of physics. Welcome to this explainer where we're going to crack that exact puzzle wide open. Today, we're unpacking the physics of interference, drawing directly from Richard Feynman's legendary lectures. We're going to take a journey together, starting from the literal anatomy of how a physical wave is first born, moving right into real-world engineering dilemmas, and finally exploring the elegant mathematical abstraction that makes all of our modern communications possible. Okay, let's dive right into this. Here is our roadmap. 1. Birth of a wave. 2. The energy of radiation. 3. 2 antennas are better. 4. Sharpening the signal. And 5. The math of interference. Simple enough, let's get into it. Starting with Section 1, Birth of a wave. Because before we can steer a signal across the world, we really have to understand the absolute simplest physical case, which is how a wave is initially created by a single accelerating electrical charge. Picture a single electrical charge just sitting there, totally still. Suddenly, it accelerates upwards, then rapidly decelerates and stops. That specific abrupt motion, that's the spark. That is the physical event that actually creates the wave we want to study. And this brilliantly illustrates what happens next. The electric field moving through space is quite literally a reversed snapshot of the acceleration we just talked about. Because of the delay it takes for the field to propagate outward at the speed of light, the field moving through space is essentially a mirror image of the charge's historical motion. That outward moving delay, that is the wave itself. Now, to actually manipulate these waves, we need 2 specific tools in our toolkit. First is wave number, represented by the letter K, which measures how much the wave's phase shifts as you move through space. And second is wavelength, or lambda, the physical distance of one complete wave cycle. Keep these in your back pocket because they're absolutely crucial for understanding interference. All right, moving to Section 2, the energy of radiation. Now that we've birthed our wave, we need to shift our focus to how these newly born waves carry energy endlessly through space. So, you probably know that an electric field gets weaker the further away you get from the source. Specifically, it drops inversely with distance, or 1/r. So the wave gets weaker, right? Well, yes, but imagine the energy flowing outward within a cone. While the field itself drops, the area of that cone is actually growing by the square of the distance. And since the kinetic energy a wave can deliver is proportional to the square of the electric field, those 2 factors perfectly cancel each other out. The energy flowing within that specific cone is totally independent of how far away you are. The energy is never lost, it just continuously spreads over a larger effective area. Which brings us to Section 3, 2 antennas are better. We know how a single wave acts, and we know it carries energy forever. So let's transition from that foundational physics to the real-world application of multiple interacting waves. Here is our practical radio dilemma. Imagine you need to broadcast a signal to Hawaii. How do you pull that off without wasting half of your precious power blasting a signal completely backward towards Easter Island? If you just use one antenna, the energy spreads out everywhere. We desperately need to direct it. Let's start by putting up 2 antennas, spacing them half a wavelength apart, and oscillating them completely in phase, meaning they push and pull at the exact same time. Viewing this from above, looking west towards our destination, the fields add up. We get double the field strength, which actually means 4 times the energy. But look at the opposite side. It's completely symmetrical. We successfully boosted our power, sure, but we are still symmetrically wasting all that energy in the exact opposite direction. But here is the plot twist. What if we space the antennas a quarter wavelength apart and physically delay the phase of one by a quarter period? In one direction, say south, the signals arrive 180 degrees out of phase. They completely cancel each other out. Zero energy. But north, the built-in timing delay perfectly compensates for the physical distance delay, meaning the two signals appear exactly in phase. We get 4 times the energy going north and 0 going south. We just solved the dilemma. We didn't have to move a single piece of metal to do it. All right, section 4, sharpening the signal. We've directed the beam, but as you might have noticed, it's still spread over a really wide angle. So now we face the next inevitable engineering challenge, focusing this directed beam to be razor sharp. Now, what's really interesting here is what happens when we pull those two antennas much further apart, say 10 wavelengths apart. Right in the center, we get a beautifully sharp beam. Just a tiny angle away, the waves arrive out of phase and cancel out to 0. But we hit a new problem. If you keep moving your angle, they sync up again. So while wider spacing absolutely gives us a razor-sharp beam, it accidentally spawns all these unwanted lobes or extra beams shooting off in other directions. To fix this, we have to reveal the ultimate solution, the antenna array. By filling in the gap with intermediate antennas, placing them every 2 wavelengths and driving them all in phase, the center beam becomes incredibly powerful. We're talking 36 times the intensity of a single antenna. But more importantly, the intermediate antennas cause those off-angle signals to push and pull against each other. When antennas 1 and 6 push together, antennas 3 and 4 push together in the opposite phase. It nearly erases the unwanted bumps. We've effectively created a sharp, powerful, laser-focused beam. And finally, section 5, the math of interference. We've solved the engineering challenges, so let's pull back the curtain and look at the mathematical machinery that allows physicists to perfectly predict these exact patterns. Everything we just explored relies on 2 firmly contrasting mechanisms. Constructive interference is when waves are pushing together, their phases align, and the energy amplifies to create those bright, powerful beams we want. Destructive interference, on the other hand, is when the waves are pulling apart. Their phases are exactly opposite, creating those absolute dead zones we just examined. I absolutely love how Feynman puts this in his lecture. He says, if the interference term is positive, we call that case constructive interference, horrible though it may sound to anybody other than a physicist. It really highlights how we repurpose ordinary language in science. Normally, interference implies a hindrance, right? But here, constructive interference is literally the greatest tool we have to amplify our signal. Now, to calculate this interference, physicists use 3 specific mathematical lenses. First is the trigonometric method, second is the geometrical method, and third is the analytical method. Let's look at the geometrical method for a second to see how this builds. Any cosine wave can be thought of as the horizontal projection of a rotating vector. If we have 2 vectors representing our 2 waves, both rotating counterclockwise like a rigid body, we just add the vectors together using the ordinary parallelogram rule to get a resultant vector in the middle. It perfectly, elegantly visualizes how 2 waves with different phases add up to create an entirely new amplitude and a new phase. And when using the analytical setup, solving for interference ultimately boils down to finding one simple thing: the total phase difference between signals arriving at a distant point. You literally just take the delay caused by the physical distance difference, add any built-in timing delay between the 2 oscillators, and boom, you have the exact interference pattern. It's just that straightforward. So the crucial point we're taking away here is this: interference isn't just some abstract quirk of physics. It is the fundamental mathematical mechanism that allows us to direct energy where it actually needs to go, preventing us from indiscriminately wasting power into the void. It is the lifeblood of how every single modern antenna array functions. Which leaves us with one seriously mind-bending physical reality. We learned earlier that the energy from these waves is never truly lost. It's just spreading continuously. So, where's the unabsorbed energy of every radio broadcast you've ever made currently traveling out in the cosmos? It's still out there, spreading forever into the universe. Thank you so much for joining me for this explainer. I really hope this sparks some curiosity for you, and I'll catch you next time. Welcome to The Explainer. Today, we are going to decode one of the most fascinating and honestly beautifully visual phenomena in all of physics, the geometry of waves.
Specifically, we'll be looking at diffraction, and we're going to do it through the legendary lens of Richard Feynman, pulling directly from Chapter 30 of his famous lectures. Now, instead of getting completely bogged down in abstract algebra, Feynman does something incredibly intuitive here. He uses simple geometry, literally just visualizing waves as little arrows to show us exactly how light behaves, bends, and interacts. By the time we wrap up, you're going to look at everything from a simple shadow on your wall to a giant space telescope in a completely new way. Let's get right into it.
Here is our quick roadmap for today. We'll hit 1. The nature of diffraction. 2. Adding waves as arrows. 3. The diffraction grating. 4. Resolving power and telescopes. 5. The weirdness of shadows. And finally, 6. The physical meaning. So, Section 1, the nature of diffraction. To really grasp what we're talking about today, we first need to tackle a pretty common misconception. If you've studied any physics at all, you've definitely heard the terms interference and diffraction thrown around to describe how waves behave. But I want you to think about this for a second. What is the exact fundamental difference between interference and diffraction? Like, if two waves bumping into each other is interference, at what precise point does it suddenly become diffraction? Well, here is Richard Feynman's incredibly candid and maybe slightly surprising answer. He says, no one has ever been able to define the difference. It is just a question of usage. That's right, there's literally no deep physical difference between them. As a general rule of thumb, when there are only a few sources, say two waves interacting, we call it interference. But if there's a huge number of them, we just switch to using the word diffraction. Under the hood, though, the underlying physical mechanism is exactly the same. It's all just the mathematics of adding waves together. Moving on to Section 2, adding waves as arrows. This brings us to the core visual metaphor of our entire explainer. Since diffraction is really just adding up a ton of waves, how do we actually do that without getting totally lost in pages of equations? Well, imagine a linear array of tiny antennas arranged in a perfect row, all vibrating and sending out waves. If we look at these waves from an angle, the wave from the second antenna has to travel just a tiny bit farther than the first one. That creates a time delay, or what we call a phase shift. Now, Feynman's brilliant trick is to represent the wave from each antenna as an arrow. The length of the arrow is how strong the wave is, and its angle is that phase shift. To add them all up, you just snap the arrows together, head to tail. If there's a phase shift between them, the arrows will naturally start to angle away from each other, basically tracing out the edges of a polygon. Okay, so what's absolutely fascinating about this graph is seeing how that simple arrow math translates into physical reality. When you look straight on at the antennas, there's zero delay. All our arrows point in the exact same direction, and they stack up into a massive, sharp central peak of intensity, that huge spike you see over on the left. But as you shift your viewing angle, that phase shift kicks in. The arrows start turning. Eventually, they curl all the way around into a perfectly closed circle. And when the arrows loop back to the starting point, the total sum is zero. You get a dark spot, a minimum. As you keep increasing the angle, the arrows just keep spiraling around and around, which creates those tiny, weak little bumps or side lobes you see tailing off to the right. So you end up with one brilliant, intense beam of light and near zero intensity almost everywhere else. All right, Section 3, the diffraction grating. Let's see how this geometric toolkit we just built turns into an incredible piece of real-world technology. We did this with antennas, right? But can we do it with visible light? Absolutely. We use a tool called a diffraction grating. You basically take a piece of glass and carve thousands of microscopic, perfectly parallel scratches into it. And when you do that, each of those tiny notches acts as a brand new little scattering antenna for incoming light waves. This image perfectly captures the geometry at play here. The light comes in, hits those parallel scratches, and scatters back out. Because of the exact spacing between the scratches, the light leaving at specific angles naturally creates a precise geometric path difference and therefore our old friend, the phase shift. But here's the kicker. The angle you need to get all those light arrows to line up perfectly actually depends on the wavelength of the light itself. So a diffraction grating will bounce red light out at a slightly different angle than blue light. It's essentially an exquisitely precise tool for sorting light into its separate colors. Which leads us straight into Section 4, resolving power and telescopes. Now we get to take these exact same wave geometries and point them up at the heavens to see how we resolve distant objects in space. Whether you're using a grating to separate colors or a telescope to look at two stars right next to each other, the wave nature of light means you don't get perfect little dots. You get a blur, a peak of intensity. So the big question is, how close can two stars be before they just mush together into one unrecognizable blob?
Rayleigh's criterion gives us a visual answer. It says we can reliably distinguish two separate wave sources if the maximum peak of one pattern falls exactly on the first minimum, that dark 0 point we talked about earlier, of the other pattern. If they get any closer than that, our instruments just can't tell them apart.
So the really crucial takeaway here is that a parabolic telescope mirror pointing at the sky acts exactly like our flat array of antennas down on the ground. The resolving power, meaning the smallest angle it can actually see, is basically just the wavelength of the light divided by the length of the array. But if you look closely at the telescope equation, you'll spot a brilliant little adjustment. We multiply it by 1.22. Why? Well, it's actually super simple. A circular telescope mirror gathers less signal at its rounded edges compared to a square array. That's it. It's the exact same wave geometry, just slightly tweaked to account for a circle.
Let's look at Section 5, the weirdness of shadows.
We've seen how nicely waves add up to create sharp beams of light. But when light runs into a simple, everyday obstacle, this wave addition creates some deeply counterintuitive stuff. Imagine a distant light source shining straight past opaque edge, casting a shadow on a screen. Everyday common sense tells us that outside the shadow it should be brightly lit, and inside the shadow it should be pitch black, right? Just a perfectly sharp line. But when we look extremely closely at that boundary, the wave nature of light has a very weird surprise waiting for us. Because the light source is hitting a screen at a finite distance, the phase delays of those waves don't just increase steadily anymore. They actually increase as the square of the distance from the edge. When we draw our little head-to-tail arrows for this scenario, they don't form a neat closed circle. Instead, they form this absolutely magnificent shape you see on the left, known as Cornu's spiral. As we add up infinite, slightly delayed wave vectors, the resulting intensity, which is mapped out on the right, doesn't just instantly drop to 0. Actually, as you approach the shadow, the brightness overshoots, wobbles, and oscillates up and down before it finally settles into darkness. So yeah, even the simple shadows on your wall are governed by the geometry of spiraling wave vectors.
Finally, Section 6, the physical meaning.
Let's bring all this spiraling geometry and complex math back down to Earth. What does this actually mean for a real physical plane of oscillating charges? Let's say we want to calculate the total electric field from a massive, infinite flat plane of charges. We do the math by adding up the wave contributions from every ring of charge moving outward, drawing our little arrows again. But because the plane is mathematically infinite, the arrows never stop. They just keep tracing out a circle, going round and round endlessly. The pure math actually fails to give us a definite answer here because an infinite plane just keeps throwing more vectors at us.
But here is where physical reality steps in and rescues the pure math. In nature, an absolutely infinite plane of charges simply does not exist. Eventually, any real sheet of material has an edge. It has to stop, or the charges must gradually taper off as you get ridiculously far from the center. And because those charges taper off, the arrows we're adding up get shorter and shorter. This physical tapering literally forces that endless, infinite circle to tighten into a spiral that settles perfectly at its exact center. So the physical constraints of nature neatly solve the mathematical infinity, handing us a precise, real-world measurement. It's brilliant.
And that right there is the true magic of diffraction. By simply treating light as little arrows and adding up their lengths and angles, we can completely decode how telescopes resolve stars, why shadows wobble, and even how nature naturally handles its own infinities. And it leaves us with a truly profound thought to chew on. If all of our vision and literally all of our astronomical instruments rely entirely on these shifting, interfering wave geometries, what invisible structures in the universe are out there right now, just waiting for us to build the precise, perfectly spaced grating required to finally see them? Thank you so much for exploring the geometry of waves with me today. Welcome to The Explainer. So today, we're taking a journey straight into the brilliant mind of Richard Feynman, specifically diving into Chapter 31 of his famous Lectures on Physics. We're going to tackle a topic that sounds pretty simple on the surface, but actually hides in an incredibly beautiful, totally counterintuitive, microscopic world. We are talking about the origin of the refractive index. We've all been taught that light travels at a strict, ultimate speed limit in a vacuum, nearly 300,000 kilometers per second. But we're also taught that when light enters water or glass, it slows down. But hold on a minute. Does the fundamental speed limit of the universe just magically change the second it hits a pane of glass? I mean, do the photons suddenly just put on the brakes?
All right, let's dive right into this. The macro perspective, the stuff we all learn in high school physics, goes something like this. When wave crests arrive from a vacuum onto the surface of a block of glass, they have to physically fit properly at that boundary. Because the wave's frequency stays the same, the absolute only way for those crests to stay matched up if the wave is moving slower is for the wave to change its angle. This is Snell's law. It perfectly describes the bending of light rays. And that brings us to our baseline definition, the index of refraction, denoted by the letter n. It represents this apparent slower velocity of light or electrical waves passing through a transparent material. If a material has an index of 1.5, light appears to travel 1.5 times slower through it. But notice I keep emphasizing the word appears, because at a physical, microscopic level, something entirely different is happening. So here is our roadmap for today. We'll logically build this complex idea step by step from first principles. We'll start with the microscopic electron dance, see how that creates a phase shift, explore dispersion and bending colors, look at complex indexes and absorption, and finally unmask the diffraction illusion. Section 1. The microscopic electron dance. Let's reveal the microscopic machinery operating right behind the glass. Feynman sets up a couple of absolutely critical, unshakable rules here. First off, the original wave always travels at the ultimate velocity, c. It never slows down, like ever. Second, when that original electric field hits the atoms in the glass, it exerts a physical force on the electrons. Think of these electrons as being fastened to their atoms by tiny, invisible springs. The incoming wave literally drives them up and down. And what happens when you accelerate a charge? It generates a brand new electromagnetic field. So the total field we actually see on the other side of the glass is the original field plus this newly generated field. Visualizing this elegant concept really helps. A source generates an arriving electric wave. It hits the glass plate. Boom. The electrons inside that plate start wiggling and they radiate a brand new wave. The transmitted wave that comes out the other side is simply the original wave plus the new wave. Both of these waves are traveling at the absolute speed of light, but somehow when they add together, they totally fool our eyes into seeing one slower wave. So how does that work? That brings us perfectly to section 2, creating the phase shift. We need to look at the mathematical trig of how these two waves combine. Think of our original wave as a vector, essentially a push, pointing straight ahead. Now, the math shows us that the new wave generated by those wiggling electrons doesn't line up perfectly with it. It actually pushes at a right angle. And when you add a perpendicular push to your main wave, you rotate the total vector. The resultant combined wave is shifted by an angle. This angle is a delay in phase. The crest of the combined wave arrives slightly later than the crest of the original wave would have. The waves didn't actually slow down, but their combination creates a phase delay that perfectly mimics a slower wave. Mind-blowing, right? Now that we know how the illusion of slower light is created, let's introduce different colors in Section 3, Dispersion, bending the colors. Because our electrons act like weights on little springs, they have a natural resonant frequency, basically a speed they want to wiggle at. If the incoming light is a high frequency, like blue light, it wiggles the electrons differently than a lower frequency red light would. For most transparent things like air and glass, the index of refraction rises slowly with the frequency of the light. This is called normal dispersion, and it's exactly why a prism bends blue light more than red light, giving us rainbows. But there is also anomalous dispersion, where the index drops sharply. Now, what's really interesting is what happens right at that anomalous dispersion point. When you graph this out, you see these massive, dramatic spikes. When the frequency of the incoming light gets extremely close to the atom's natural resonant frequency, the electrons just go wild. The index of refraction spikes massively, and just past the resonance, it actually drops into a negative slope. In fact, if we beam X-rays into glass, the index of refraction actually drops to less than 1. Now, wait a minute, you might be thinking, does that mean the wave travels faster than the speed of light? No way! When you chart a wave signal turning on, you see that while the nodes, the mathematical crossing points of the wave, can appear to be advanced and travel faster than c, the actual start of the signal, the very first transient motion when you turn the wave on, never ever breaks the ultimate speed limit. You literally cannot send a signal faster than light, even if the wave's phase nodes play tricks on you. Let's take our mathematical formula a step further in Section 4, Complex Indexes and Absorption. Let's see how adding some real-world friction builds our understanding even more. Real atom springs don't just bounce perfectly forever, right? They have a damping force, a friction.
To account for this, Feynman introduces a complex number into the index of refraction, represented by I. The index n now has a real part and an imaginary part. So what does an imaginary index of refraction actually mean in reality? Well, it means absorption. That friction weakens the wave as it travels through the material, converting the lost electromagnetic energy into heat. And here is why this matters on a massive cosmic scale. Because atoms absorb light strongly at their specific resonant frequencies, they leave dark lines in the light spectrum. By looking at sunlight or starlight and finding those exact dark absorption lines, we can perfectly reveal the chemical makeup of the distant universe. And it's all because of this microscopic friction.
And that sets us up for our final application, Section 5, the diffraction illusion.
I want to challenge your common sense again here. What exactly is an opaque screen? If you put a thick piece of metal between a light bulb and the wall, you get a shadow, obviously. But why? Your brain says, well, the light hits the metal and stops. But based on the exact first principles we just established, the original light wave never stops. It keeps going right through the metal. So why is it dark behind the screen? Walk through Feynman's incredible argument with me here. The source wave hits the screen. It drives the electrons in the screen to wiggle. Those wiggling electrons create a new wave. Because the screen has a high imaginary index of absorption, those wiggling electrons generate a new field that is perfectly opposite to the source field. The total field on the backside is the source wave plus the screen wave, and they perfectly cancel each other out to zero. An opaque screen is really just a wall of wiggling electrons desperately shouting out a wave that cancels out the light. And this leads to an absolute stroke of genius for understanding diffraction, which is what happens when you poke a hole in that screen. Feynman says, the field at P when there are holes in a screen is the same as the field produced by that part of a completely opaque wall, which is located where the holes are. Think about that for a second. The wall cancels the source. The hole doesn't cancel the source. Therefore, the light coming through the hole is mathematically identical to the light that a solid plug would have radiated to cancel the source. It's this amazing backwards-forwards argument that completely justifies how we calculate diffraction patterns. So, let's summarize the journey we've taken in this explainer today. We started with the pretty naive macro view that light just gets tired and slows down in glass. But we unmasked it using 3 struct steps. 1, we acknowledge that the speed of light, c, is always constant. 2, we calculate the wiggling of the electrons driven by the source. And 3, we add that new electron wave to the source wave, discovering that they form a resultant wave whose phase is delayed, beautifully mimicking a slower speed. It's a huge testament to the fact that the universe is rarely as simple as it appears on the surface. Which leaves me with this final thought for you to ponder today. If the slowing down of light, something that is literally taught in every introductory science class, is actually just a complex mathematical illusion created by dancing electrons, what other simple rules of physics that you interact with every single day are just microscopic illusions waiting to be unmasked? Keep questioning the obvious, and thanks for exploring with me.
Welcome to this explainer. Today, we're jumping right into a deep dive on the fascinating physical mechanics of radiation damping and light scattering. We'll be focusing entirely on the brilliant insights laid out in Chapter 32 of the Feynman Lectures on Physics, really unpacking the physical meaning behind how energy radiates from microscopic charges to create the world we see around us.
We've all wondered it at some point, right? Why do clouds look white while the sky looks blue? It's a question kids ask all the time, but the answer is wild. It literally starts at the absolute smallest scale, with just a single vibrating electron. So let's dive into this and see exactly how the math of a tiny charge ends up painting the entire sky.
Here's a quick look at our agenda for today. The resistance of radiation, calculating radiated energy, independent sources and interference, scattering light and blue skies, white clouds and red sunsets, and finally, the secret of polarization.
All right, let's kick things off with Section 1, the resistance of radiation and holding back by bootstraps.
So when a charged body accelerates up and down, it radiates energy. And, to conserve energy, work has to be done, which creates a sort of resistance. Feynman had this brilliant way of putting it. He pointed out that an electron actually has physical dimensions, so an action across it isn't instantaneous. There's a slight delay. Because of this, if an electron is accelerating, the force acting on its front isn't perfectly balanced with the force on its back. This essentially forces the charge to resist its own motion. It's literally holding itself back by its own bootstraps.
Now, because of this radiation resistance, an oscillating electron isn't going to just vibrate forever. It slowly loses juice.
We measure this decay using something called the Q factor, which is basically the total energy of the system divided by the energy lost per radian of oscillation. Take a freely emitting sodium atom, for instance. It'll typically oscillate for about 10 million radians before its energy really drops off. And the craziest part, that entire process takes just 10 to the -8 seconds.
Moving right along to Section 2, calculating radiated energy, or what we like to call the math of the vacuum. So, how do we actually calculate that energy blasting out into space? We'll take a look at this exact number, 377. That's 377 ohms, the impedance of a vacuum. It's an absolutely crucial constant. If you ever need to figure out the power in watts passing through a square meter of empty space, you just take the average of the electric field squared and divide it by 377. Simple as that.
But hey, calculating power in just one direction doesn't give us the whole picture. To get the total radiated energy, we've got to integrate that power over an entire sphere. It's kind of like a giant math puzzle. We start by finding the area of a tiny annular segment, calculate the energy flowing through that little slice, and then mathematically sweep it across the whole sphere to capture every single drop of power.
And once you crunch those numbers and do that complex integration, you're left with this beautifully simple rule. The energy liberated relies entirely on the average squared acceleration of our oscillating charge over a full cycle. Basically, the harder that electron shakes back and forth, the more energy it chucks out into the universe.
That brings us to Section 3, independent sources and interference, and keeping in phase. Now you might be wondering, what happens when you have a bunch of atoms radiating all at once? You'd probably expect this massive chaotic interference pattern, right? Well, nature actually prevents that. A single atom only radiates for a tiny fraction of a second before another one takes over. Their phases drift so fast that any interference completely averages out to zero. Lasers, on the other hand, bypass this entire issue. They literally force all the atoms to emit together, locking that phase in for much, much longer intervals.
All right, let's step up to the macro level with Section 4, scattering light and blue skies, and their microscopic origin.
Let's apply this scattering physics to the atmosphere we see every day and finally answer why the sky is blue. When a beam of sunlight hits an atom in the air, the electric field of that incoming light drives the atom's electrons up and down. Because they're being accelerated by the sunlight, they act like tiny antennas, re-radiating or scattering that energy in all directions.
And here is where the math really pays off. When we calculate the scattering cross-section for air, we find that the scattering is proportional to the fourth power of the frequency. Because of this incredibly steep mathematical relationship, blue light, which has roughly twice the frequency of red light, gets scattered 2 to the power of 4, or 16 times more intensely than red light. That is exactly why, when you look up and away from the sun, the sky above you is a brilliant, intensely scattered blue.
Which naturally leads us to Section 5, white clouds and red sunsets, and the sheer power of agglomeration.
Okay, but if water vapor is already in the air, why do clouds suddenly look so opaque and white? The secret is a process called agglomeration. Step 1, single water atoms just act like normal air, scattering light independently. But step 2 is where the magic happens. When water molecules clump tightly together into tiny droplets that are smaller than a wavelength of light, they get driven by the sunlight perfectly in phase. If you have n atoms in a clump, they don't just scatter n times the light. Their amplitudes combine, and the scattered intensity skyrockets by n squared. That exponential boost blasts all frequencies of light outward, giving us bright white clouds. But step 3, if they keep growing larger than a wavelength, they fall out of phase, which drastically shifts the color of the scattered light from blue toward red.
You can actually prove this right in a laboratory using the famous Hypla experiment. If you mix sodium thiosulfate and sulfuric acid, microscopic sulfur grains start precipitating out. At first, they're super tiny and scatter a pale blue, but as they clump and grow, the liquid turns intensely whitish. Here's the kicker though. If you look at the light source directly through the tank, all the blue has been scattered away, leaving only a deep, fiery red. It perfectly replicates exactly why sunlight passing horizontally through the thick lower atmosphere at dusk gives us those spectacular red sunsets.
Finally, let's wrap up with Section 6, the secret of polarization and vibrating one way.
There's one more really fascinating side effect to this entire scattering process. Remember, the sunlight driving the atom is unpolarized. Its electric field is vibrating in random directions perpendicular to its path. But the electron being driven, it can only vibrate back and forth along one line. Because that driven electron vibrates in the exact same direction as the incoming field, If we look at the scattered light from exactly 90 degrees to the beam, we're looking from an angle where only one plane of vibration is visible. So the light scattered at right angles is perfectly plane polarized.
And that brings us to the end of this explainer. Think about it for a second. If the grand sweeping canvas of blue skies, brilliant white clouds, red sunsets, and even polarized light is all perfectly dictated by the rigid, microscopic math of a single vibrating electron, what other everyday phenomena around you are just waiting to be decoded by physics? It's an incredible thought to leave you with, really showing how deeply the fundamental laws of nature connect to the reality we experience every single day. Keep looking up and keep questioning what you see.
Welcome to this explainer. Okay, so today we're looking at something you literally experience every single waking second of your life, yet you might actually fundamentally misunderstand it. We are talking about color. Based on the absolutely incredible lectures of physicist Richard Feynman, we are going to completely reframe how you think about the vibrant world around you. As you'll see, color is not actually a strict physical reality living out there in the world. Rather, it is this magnificent biological illusion constructed directly by your eyes and your brain. To make sense of all this, we've got a clear master plan today. We'll be covering inside the human eye, seeing in the dark, the math of color mixing, the chromaticity diagram, clues from colorblindness, and finally, the chemistry of color. Let's get right into it. Okay, let's dive into this. Think about it for a second. Does color actually exist out there in the physical world, or is it just this grand illusion crafted by your mind? I mean, sure, physics can measure the exact wavelength of light bouncing off a shiny red apple, but here's the thing. That wavelength isn't inherently red. Red is a sensation. It's totally an interpretation. So to really understand where color comes from, we gotta start at the absolute gateway of perception. Section 1. Inside the human eye, the hardware of vision. Let's take a quick look at the physical components that actually make all of this possible. Everything starts at the retina. Now, you might kind of think of the retina as just, a dumb screen at the back of the eye that just blindly passes a picture along to the brain. But Feynman points out something absolutely amazing here. The retina is already thinking about the light. It's this incredibly complex network of cells that actively digest information, literally comparing spots of light horizontally right there across the eye before it even bothers sending a single signal to your optic nerve. Just follow the path of the light here. It enters right through the cornea at the top, passes through the lens, and then hits the retina at the back. See that little tiny depression right in the center? That's the fovea. That's where our vision is at its absolute sharpest, where we naturally focus when we want to see super fine detail. And then check this out. Right below it, where the optic nerve exits, there are literally no light-sensitive cells there at all. It creates an actual literal blind spot that your brain just smoothly edits out for you. Section 2. Seeing in the dark, the Purkinje effect. Now that we've got the hardware down, let's see what happens when our biology completely shifts gears in low light. So our eyes have this brilliant division of labor going on. Basically, we've got two main types of light-sensitive cells, rods and cones. Cones, they're the bright light specialists. They give us that sharp central focus at the fovea, and they let us see in full, glorious color. Rods, on the other hand, are your low-light heroes. They populate our peripheral vision and are incredibly sensitive. But, and here's the kicker, they see absolutely zero color. Imagine this. You take a brightly colored magazine into a pitch-black closet, right? Then you slowly let just a tiny sliver of light in. Because your rods are fully taking over, those bright, vibrant reds will suddenly look pitch black to you, while blues might actually look surprisingly light. This wild shift in how bright things seem, that's called the Purkinje effect. And this brilliantly illustrates exactly what's happening. Just look at the difference in these curves. That solid curve right there shows your cone sensitivity in normal daylight, peaking really nicely right in the yellow region. But then look at the dashed curve. That's your dark adapted vision, relying entirely on your rods. It peaks way over in the green, and if you follow that dashed line all the way over to the right side where the red light lives, it just completely drops to zero. Your rods are completely 100% blind to deep red light. Section 3. The math of color mixing, the eye as a null instrument. Okay, let's pivot from biology into this strangely fascinating, abstract math of color. When scientists study how we perceive color, they use the eye as what's called a null instrument. Meaning, they don't ask you how you feel when you see the color green. They just ask you to adjust two lights until they look perfectly identical. And through this, they discovered 3 absolute game changers. First, literally any color can be matched by mixing 3 primary lights, say red, green, and blue. Second, once two colors match to your eye, they stay matched, even if your eye gets super tired or adapts to a completely different light. But man, the third point is where it gets wild. To match certain colors, you actually have to cheat. If you can't quite match a color, you literally have to shine one of your primary lights onto the target color to wash it out. You're effectively moving it to the other side of the math equation, acting exactly like negative light. So the absolutely crucial point here is that matching colored lights is purely a mathematical proposition. It is completely mathematically identical to adding vectors in a three-dimensional space. If you want a specific color, you just add specific amounts of your three primaries. It's just this elegant, breathtaking mathematical formula, and it's happening effortlessly, constantly, right inside your head. Section 4. The chromaticity diagram, mapping the visible world. Because hey, if color mixing is really just vector math, we should be able to graph it, right? Now, what's really interesting about this is those dips right below the zero line. This is graphing the exact amounts of red, green, and blue light needed to match every pure color of the rainbow. See how those curves dip down into the negative? That definitively proves that there is no such thing as a perfect, absolute set of three primary colors in nature. You just can't make every single hue without eventually having to dip into negative light. But by taking all that super complex vector math and projecting it down onto a simple, flat plane, scientists were able to create a sort of master map. They proved that every single color visible to the human eye lives completely, neatly inside one specific mathematical boundary. And here is that map, the legendary standard chromaticity diagram. See that curved horseshoe boundary? That outlines the pure physical spectral colors, starting from extreme violet way down at the bottom left, swooping all the way up and around to extreme red on the far right. Any color you can possibly perceive, whether we're talking about the delicate pink of a rose or the deep, rich brown of tree bark, lives somewhere inside that exact shape. And if you mix any two colors, you just draw a straight line across the space inside this horseshoe, and boom, there's your new color. Section 5. Clues from color blindness. Reverse engineering vision. So how did scientists actually prove the eye uses three distinct pigments to do all this math? Well, they used mistakes. Let's see how this all builds together. Here we have maps showing colors that look identical to individuals with two very specific types of color blindness. We've got deuteranopes on the left and protonopes on the right. Because these folks are missing one of the three color pigments in their eyes, colors that look totally distinct to us actually fall right along these identical straight lines for them. And then, mathematicians realized something incredible. By extending these lines of confusion, they found that they all intersect at one specific focal point. Those intersecting points mathematically exposed, with perfect precision, the exact absorption spectra of the pigments that were missing from the human eye. Talk about reverse engineering at its finest. Section 6. The chemistry of color, visual purple and beyond. Let's bring it all home and look at the ultimate physical proof, found right in the literal chemistry of the eye. Just take a look at this absolutely beautiful convergence of biology and chemistry. The dots you see here, they represent the actual chemical absorption of a pigment they extracted from the eye, a pigment called visual purple. And get this, it was discovered way back in 1877. Now look at the solid curve running exactly through those dots. That represents our eye's ability to see in the dark. It is a completely perfect match. Visual purple is the literal, exact chemical that our rods use to see when the lights go down. As Richard Feynman so perfectly put it, and I absolutely love this quote, it is very important to appreciate that a retina is already thinking about the light. It is comparing what it sees in one region with what it sees in another, although not consciously. Honestly, it's just incredible. A purely physical photon hits your eye, but the actual psychological sensation of color, that is built entirely by this quiet, totally unconscious processing. Which leaves us with this final, genuinely mind-bending thought. If our eyes are actively constructing the very reality of color before the signal even reaches our conscious brains, what else around us is just a beautiful illusion? Next time you look up at a vibrant blue sky or stare at a bright red stop sign, just remember, that color doesn't actually live out there in the world. It lives entirely inside you. Thank you so much for joining me for this explainer, and always keep questioning what you see.
Welcome to this explainer on the mechanisms of seeing. You know, when most of us think about our eyes, we usually imagine a pretty simple piece of biological hardware. Essentially a passive camera lens just capturing light and sending a raw video feed straight into the brain. But in Chapter 36 of his lectures on physics, Richard Feynman completely flips this idea on its head. He shows us that your eye is actually an active, wildly complex computer that is literally reaching out and interacting with the outside world. Today, we're going to unpack this entire process, using Feynman's own figures to grasp the deep, physical meaning behind how we actually see.
Let's just dive right into a seriously mind-bending example of the eye doing calculations on the fly. We have a simple black and white disk. It is entirely monochromatic. But inexplicably, when this exact disk is spun, distinct colors suddenly appear in the rings. And if you reverse the spin, the colors actually switch places. Crazy, right? This happens because seeing isn't just about absorbing light. It involves elementary computation happening right there in the eye itself, long before your brain even gets a memo. Your visual system is actively putting pieces of temporal information together and constructing the sensation of color out of thin air.
To really wrap our heads around this incredible process, we're going to break it down into 4 main parts. First, the brain looking outward. 2, the chemistry of sight. 3, the physics of the compound eye. And 4, computing the visual world.
All right, part 1, the brain looking outward, specifically looking at our anatomical wiring and the optic chiasma.
So let's start with a totally surprising physiological truth. Your retina is quite literally a piece of your brain. During embryonic development, the brain essentially pushes out a small piece of itself just to develop a way to look out upon the world. But fascinatingly, it's built inside out. The light-sensitive receptors are tucked behind multiple layers of other cells, meaning light actually has to pass through the wiring before hitting the sensors. It's a wildly complex web of neural interconnections moving from the eyes down into the brain. Notice how the optic nerves from the left side of each eyeball actually cross the optic chiasma to the left side of the brain? This completely splits our visual field right down the middle. Everything on the right side of your visual field goes to the left hemisphere and vice versa. Your brain then has to stitch this violently split feed back together just to give you normal binocular vision.
Now, since the eye is basically an extension of the brain performing calculations at the source, early researchers realized that color vision couldn't just be a simple, raw feed of red, green, and blue. So they proposed what's known as the opponent theory of color. This theory hypothesizes that instead of sending raw data, the nerve fibers actually carry conflicting, opposing signals, like yellow versus blue or red versus green.
The mechanics of this are brilliant. In these mathematical models, photochemical absorptions are actually wired to physically subtract signals from one another. So, if a nerve is firing heavily for yellow, it actively decreases the signal for blue. This hardwired math perfectly explains a really weird psychological quirk. It's exactly why we can easily imagine a yellowish green, but literally no one can picture a reddish-green hue. The signals mutually exclude each other right at the hardware level. Moving on to part 2, the chemistry of sight and the quantum shifts happening right inside your eye.
Now that we've looked at the macroscopic wiring, let's zoom in, like a million times closer, microscopically into the rod cells to discover the actual physical chemistry of vision. How exactly is a completely massless photon translated into a biological electrical signal? Well, deep inside the visual purple pigment of your eye sits this vital molecule called retinine. It features a conjugated chain of alternating double bonds along its side. In physics and chemistry, this specific structure is notorious for absorbing light intensely.
Think of those alternating double bonds like a tightly packed row of dominoes. When a photon strikes the molecule, an extra electron at one of the double bonds gets bumped over just one tiny step. But that instantly causes all the other electrons in the chain to shift, producing a massive cascading effect. Instead of just moving an electron a tiny atomic distance, the chain reaction moves the electrical charge across the entire molecule, firing a strong, clear electrical signal straight to the optic nerve.
Here's the kicker, though. Human bodies completely lack the ability to make this magical molecular domino setup natively in our cells. We literally have to eat it. We consume it in the form of vitamin A, which is almost chemically identical to retin A. If you don't get enough vitamin A, you lose the retin A in your rod cells, the dominoes disappear, and you suffer from night blindness. So this isn't just a fun anatomy fact. It is basic quantum chemistry keeping the lights on in your head.
Let's jump to part 3, physics of the compound eye. We're talking the mathematical perfection of insect vision.
We're leaving human chemistry behind and shifting our perspective to the animal kingdom, specifically the bee, to see how natural selection solved a fiercely complex optics problem using pure, calculable physics. A bee's eye is a compound eye, radically different from ours. It doesn't have one big lens.
Instead, it's made up of thousands of these conical cells called ommatidia. They act like tiny little light pipes, grabbing light from a narrow angle and filtering it down a central nerve fiber. But evolution had a serious physics problem to solve when deciding exactly how wide to make these cones.
Nature faced a brutally strict mathematical trade-off. On one hand, you have visual resolution. If the ommatidia are too large, the bee has terrible, chunky, pixelated vision. It needs small, tightly packed cells for detail. But on the other hand, you have light diffraction. If a hole is too narrow, light waves squeeze through, diffract, and scatter uselessly, blurring the image entirely. So you actually need larger cells to avoid scattering.
So how exactly did nature balance this? Well, if you map it out on an optimization curve, the absolute best visual acuity sits right at the minimum point where the geometric error and the diffraction error meet. If we use Feynman's equations for the exact wavelength of light a bee sees, the math spits out an optimal ommadium diameter of roughly 30 micrometers. And guess what? When you put a real bee under a microscope, its ommadium measure almost exactly 30 micrometers across. It is literally as if evolution sat down and did calculus to optimize insect vision.
Finally, Part 4, Computing the Visual World. This is all about lateral inhibition and how our eyes actively edit reality. To really understand how eyes don't just passively receive signals, but actively compute, enhance, and edit reality for the brain, scientists looked at the horseshoe crab. They placed microscopic electrodes into the crab's optic nerve. When they illuminated just one ommatidium, the nerve fired rapidly. But shockingly, when they turned on a light in a neighboring ommatidium as well, those original pulses actually slowed down. The mere presence of nearby light turned down the volume of the original signal. This additive interference is known as lateral inhibition, and honestly, it's a brilliant biological trick. In a uniformly lit area, all the neighboring nerves suppress each other, keeping the overall signal pretty weak. But at a boundary, like an edge where light meets dark, the nerves in the light aren't inhibited by the nerves in the dark. Because of this, the signal at the very edge is artificially maximized by the eye.
The result of this is absolutely fascinating. Right at the boundary where illumination drops off, the nerve response actually spikes up artificially high before dropping. The eye is intentionally drawing an enhanced contour. It perfectly explains why humans can instantly recognize simple line drawings or cartoons. Literal outlines don't actually exist in the physical 3D world, but our eyes are hardwired to compute and draw those lines for us anyway, before even handing the image over to the brain.
The computing complexity goes even further in a frog's eye. Frogs don't really move their eyes around. Instead, their optic nerve fibers act like specialized geometrical calculators. Frogs actually have fibers that only fire when they detect a moving convex edge against a dark background. Think about the crazy computational power required in the retina to understand that a specific dark convex curve just entered the field. Why do they need this? Because a moving dark convex curve is the exact shape of a tasty flying bug. The eye filters out all the useless noise and only alerts the brain when dinner flies by.
And as Feynman so humorously pointed out, frogs even have dedicated dark detectors. Even when there is absolutely zero light present, the eye never really rests. These specific fibers just furiously fire electrical spikes in pitch blackness, perpetually screaming to the brain, "It is dark! It is dark! It is dark!"
Which brings us to a pretty profound final thought. Knowing that the eye isn't just a simple camera, but an active computer, a literal piece of the brain editing the universe, generating outlines that don't exist, inventing colors from black and white spins, and mathematically processing shadows before our conscious mind even registers a single frame, it leaves us with a huge question. How much of the reality we see every single day is actually out there, and how much is just a brilliant, highly evolved biological illusion? Definitely something to chew on next time you trust your own eyes. Thanks so much for joining me for this explainer, and keep questioning what you see. Hey everyone, and welcome to this explainer. Today we're going to explore what is absolutely, without a doubt, the most famous thought experiment in all of physics. We're diving right into Richard Feynman's legendary chapter I-37 on quantum behavior. It's this incredible analysis that just beautifully demystifies the very core of quantum mechanics and its physical meaning. So, if you've ever felt kind of intimidated by the quantum realm, well, you're in the right place, because we're going to break it all down step by step together. Okay, let's dive into this with a really fundamental question. What happens when matter stops acting like matter? I mean, it sounds like a total paradox, right? But as we're about to see, the regular rules that govern everyday objects, the stuff we can literally touch and feel,
They completely break down when we zoom into the atomic scale. This is the big mystery we're unraveling today.
So here is our roadmap for today. Number 1, classical particles. Number 2, classical waves. 3, the electron riddle. 4, watching the electrons. And 5, the uncertainty principle. Let's get to it.
Starting right off with Section 1, classical particles, and the physical meaning of lumps. We really need to ground ourselves in comfortable everyday physics before we start breaking all the rules.
Imagine our first home base. We've got a machine gun and it's just randomly spraying bullets toward a wall of armor plate. Now this wall has 2 holes in it, hole 1 and hole 2. Beyond that is a wooden backstop and a movable detector to catch the bullets. Let's assume these are completely indestructible bullets. They cannot break in half, they always arrive as whole, distinct lumps, and they arrive exactly one at a time. If you hear a thud in the detector, you know you caught exactly 1 complete bullet. Simple enough, right?
So if we want to know the probability of a bullet arriving at any specific spot on the backstop when both holes are open, well, the math here has a very simple physical meaning. The total chance of a bullet hitting a spot, we'll call that P12, is just the sum of the probabilities from each individual hole. You literally just calculate the probability of the bullet going through hole 1, add it to the probability of it going through hole 2, and that's the whole shebang. P1 plus P2. There's no interference, bullets are lumps, and their probabilities simply add together.
Okay, let's move to Section 2, classical waves and the physical meaning of interference. We're going to swap out our lumpy bullets for something entirely different.
We've now replaced that machine gun with a wave source, jiggling up and down in a shallow trough of water. The wall with the 2 holes is still there, but instead of that smooth curve of probabilities adding together, the intensity of the waves hitting our detector has these massive high peaks and really low valleys. The pattern is just completely different, and this brilliantly illustrates how waves behave in a physical space.
So why does this happen? Well, unlike our indestructible lumpy bullets, waves are continuous. When those circular waves ripple out from hole 1 and hole 2, they actually run right into each other. If 2 wave peaks arrive at the exact same time, they add together to make an even higher peak. That's constructive interference. But if a peak meets a trough, they cancel each other out. Destructive interference. So the total intensity at the backstop is absolutely not just the sum of the 2 holes. Waves interfere. Keep this rule in your back pocket because things are about to get really strange.
So we've established our baseline, right? Particles arrive in lumps and add together. Waves are continuous and interfere. Now for Section 3, the electron riddle. Prepare to see the rules of reality completely broken.
Now, what's really interesting about this slide is that this setup looks like a totally bizarre crime scene. We've replaced the machine gun and the water waves with an electron gun. When we turn it on, the detector records these very distinct clicks. Click, 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 click. Every single click is identical. There's no such thing as a half click. So the electron gun is firing indestructible lumps, exactly like the machine gun firing bullets. But the resulting graph shows the high peaks and low valleys of a wavy interference pattern. It fires lumps, but they land like waves. No way, right?
This brings us to a massive, mind-bending paradox. Proposition A says that since electrons are indestructible lumps, each electron must go through either hole 1 or hole 2. But if that were true, their probabilities should just add together like those bullets did. The reality, however, is that electrons distribute themselves as if they're waves passing through both holes simultaneously and interfering with themselves. Get this, if you close one of the holes, you actually increase the number of electrons arriving at some of the valley spots on the backstop. Think about that for a second. How could closing a hole possibly increase the number of lumps getting through to a specific point?
So what does this all mean? Do the electrons split in half? Do they take some crazy, complicated path, going through one hole, looping all the way around, and flying backward through the other? Actually, no. All classical explanations completely fail us here. Every single time you measure an electron, it arrives as one whole lump. It never splits. Yet the pattern it forms over time is undeniably a wave of probability.
This leads us perfectly to Section 4, watching the electrons and catching nature in the act. If nature is pulling a fast one on us here, it's time we figure it out. We are going to find out exactly which hole these lumps are going through.
To do this, we're tweaking our experimental setup by placing an incredibly strong light source right behind the wall, right between the 2 holes. Because electric charges scatter light, whenever an electron passes through a hole, it's going to scatter a little flash of light. If it goes through hole 1, we'll see a flash near hole 1. If it goes through hole 2, a flash near hole 2.
Now we can finally see exactly where each electron goes, while also plotting where it lands on the backstop.
But here is the totally mind-bending result. I literally want to read this quote directly from Richard Feynman. When we look at the electrons, the distribution of them on the screen is different than when we do not look.
So, the crucial point is this. When we turn on the light and actually watch the electrons, we do see exactly which hole they go through. Proposition A becomes experimentally true. But the very moment we do this, the wavy interference pattern completely vanishes. The electrons go back to acting exactly like regular lumpy bullets. The probabilities just add up again, P1 plus P2. The mere act of observing the electrons literally destroys the interference pattern.
Now, you might be thinking, hey, let's just trick nature. Let's dim the light so we don't disturb the electrons as much. Well, actually, scratch that, because light also comes in lumps, photons. Dimming the light doesn't make the individual flashes weaker. It just means fewer photons are shooting out, so some electrons just slip by completely unobserved. And guess what? The unobserved electrons form a wave pattern, while the observed ones act like bullets. Okay, so what if we use a longer, gentler wavelength of light, like infrared? Well, a longer wavelength makes the flash of light physically fuzzy. The gentler you make the light, the larger and fuzzier the flash becomes, until the flash is so gigantic you can't tell if it came from hole 1 or hole 2 anymore. And the exact millisecond you can no longer tell which hole the electron went through, boom, the wave pattern returns. Nature absolutely refuses to be outsmarted.
Which brings us to our final section, the uncertainty principle. Because this isn't just a quirk of our light source, this is a fundamental limit of the universe itself.
Let's try one last purely mechanical trick. We've mounted the wall with the holes on perfectly frictionless rollers. When an electron passes through a hole and gets deflected toward the detector, it has to give the wall a tiny little kick, a recoil momentum. By measuring whether the wall gets kicked up or down, we can deduce which hole the electron went through without ever shining a single light on it. But to measure the wall's momentum change accurately, we have to know its starting momentum super precisely. And here is where Heisenberg steps in. If you know the wall's momentum perfectly, its physical position becomes uncertain. The wall jiggles, and that jiggle randomly shifts the holes, which randomly shifts the landing spots of the electrons and completely smears out the interference pattern. Once again, the pattern is destroyed.
And this leads us directly to Heisenberg's uncertainty principle. It states that it's impossible to design an apparatus to determine which hole the electron passes through without simultaneously disturbing the electrons enough to destroy the interference pattern. This isn't a technological limitation. It's not like our microscopes just aren't good enough yet. This is a basic, built-in characteristic of how nature protects the rules of quantum mechanics. Let's move to and see how this builds our understanding of the macro world. You might be wondering, if all matter acts like waves, why didn't we see an interference pattern with the machine gun bullets at the very beginning? Well, quantum mechanics says the bullets do actually have an interference pattern. But because bullets are so massive compared to electrons, their quantum wavelength is impossibly tiny. The wiggles of their wave pattern are so tightly packed together that any physical detector just straddles millions of them all at once. The rapid wiggles just blur into a single smooth average, which is exactly the classical curve we expect to see. The quantum wiggles are there. They are just impossibly small. What this all boils down to is a massive philosophical shift in science. As Feynman points out in chapter I-37, physics has officially given up on predicting exactly what will happen in a definite circumstance. If we do not look at which hole the electron goes through, we absolutely do not know what it's doing. It hasn't secretly decided which path to take, because if it had, it wouldn't create a wave pattern. We just have to accept that nature at its fundamental core only gives us the odds. We can only predict the probability.
And that leaves us with this final, amazing thought to ponder. If the universe at the smallest scales is fundamentally governed by probability, and the very act of observation forces reality to choose a definite path, what else are we missing when we aren't looking? Thank you so much for walking through this explainer with me. Keep exploring, keep asking questions, and never stop marveling at the sheer weirdness of our universe.
Welcome to this explainer. Today we're going to explore how the invisible, completely chaotic collisions of atoms actually create the precise physical laws of our everyday world. Specifically, we'll be breaking down the brilliant foundational concepts from Richard Feynman's lectures on the kinetic theory of gases.
Here is our roadmap for today. We've got 1. The invisible racket. 2. Bouncing atoms create pressure. 3. The secret of temperature. And 4. The ideal gas law. Let's get right into it.
Section 1. The invisible racket.
the macroscopic experience of invisible gases.
So let's kick things off with a question that sounds simple, but is actually pretty profound. Why can't we hear the air? If you think about it, if our eardrums were just a tiny bit more sensitive, our everyday lives would be completely overwhelmed by this inescapable rushing noise.
Richard Feynman had a brilliant way of describing this reality. He pointed out that what we calmly call air is actually a perpetual racket of tiny molecules constantly bombarding us. Luckily for us, human evolution kindly tuned out this microscopic drum solo so we wouldn't go completely crazy. But that invisible bombardment, that is exactly where physical force comes from.
Section 2. Bouncing atoms create pressure. Zooming into the microscopic world. Okay, let's visually ground this abstract idea. Imagine a box of gas with a frictionless piston on one side. As atoms zip around inside, they're constantly banging against that piston. Notice that force labeled F right here that we literally have to push back with just so the piston isn't blown right out of the box? Well, pressure is simply that exact force divided by the area of the piston. It perfectly balances the sum of countless invisible atomic collisions pushing against it.
We don't need complicated mechanics here, just some simple logic. First, an atom flies toward the piston. Bam! It hits it and reflects perfectly, bouncing back with the exact same speed. That reflection transfers just a tiny bit of momentum to the piston. Now multiply that one tiny kick by the billions of collisions happening every single second, and together they collectively create that steady, macroscopic force we measure as pressure.
And since pressure is really just the total momentum delivered per second, we can actually have two completely different microscopic situations that give us the exact same pressure. On the left side, you could have just a few atoms, but they're flying around super fast. That's a low-density, high-energy gas. Or, on the right, you could have a ton of atoms moving much more slowly. High-density, low-energy. Either way, they deliver the exact same amount of kick to our piston every second.
Moving on to Section 3, the secret of temperature, when chaotic collisions reach equilibrium.
Now, if we picture a movable piston sloshing back and forth between two entirely different gases, let's say helium on the left and neon on the right, something really amazing happens. The bangings on each side aren't perfectly uniform, so the piston jiggles. If the atoms on the left hit harder, they drive the piston into the slower atoms on the right, which physically speeds them up. It literally transfers energy through that jiggling until both sides eventually reach a balanced state of equilibrium, pouring energy into each other at the exact same rate.
And this doesn't just happen with pistons. Even if we swap out the setup for a semi-permeable membrane where the molecules can actually mix and leak through tiny holes, the end result is exactly the same. Through continuous, random collisions, the gases inevitably trade momentum and adjust their velocities to reach that exact same state of thermal equilibrium.
So what happens when individual atoms of totally different masses collide? Well, when heavy molecules and light molecules smash together, they just get sprayed around in all directions. But through millions of these chaotic collisions, a beautiful mathematical balance emerges. They eventually sort themselves out so that both the heavy and the light atoms share the exact same average kinetic energy. The lighter ones just end up zipping around a lot faster than make up for being so small.
Which brings us to a huge aha moment. Temperature is defined as the mean kinetic energy of a molecule in a gas. This is absolutely incredible to think about. What we physically experience as hot or cold isn't some invisible fluid or magical property. It is literally just the average jiggling speed of these tiny atoms. Now, thankfully, we don't have to walk around measuring the weather in joules of microscopic kinetic energy. That would be exhausting. Instead, scientists use this incredibly tiny number, 1.38 times 10 to the negative 23. This is the constant K, and it basically just acts as a handy everyday conversion factor between the raw kinetic energy of a molecule and what we artificially call a degree Kelvin on a thermometer.
All right, Section 4, the ideal gas law, zooming back out to universal equations.
To handle the sheer, mind-boggling scale of the microscopic world, chemists use this massive number, 6.02 times 10 to the 23rd. You probably know it as a mole. Instead of trying to count individual atoms one by one, using this standard batch size makes the math of predicting billions upon trillions of atoms actually manageable. And all of this brings us perfectly to the ideal gas law, PV equals nKT. That's pressure times volume equals the number of atoms times our constant K times temperature.
Because we now truly understand pressure as bouncing atoms and temperature as their average energy, this isn't just some boring equation to memorize. It's a highly logical, completely inevitable conclusion of all that microscopic chaos we've been exploring.
So let's quickly review the big takeaways here. First, gas is essentially a perpetual racket of collisions. Second, those collisions against the surface create the force we call pressure. Third, the average kinetic energy of all that atomic jiggling is what we call temperature. And finally, perfectly precise macroscopic laws emerge from microscopic averages. By tracking the physical reality of these invisible interactions, we've totally demystified the intimidating physics of how our everyday world actually works.
I'll leave you with this thought to ponder after today's explainer. If temperature is fundamentally just the physical motion of atoms, what happens when that motion slows down so much that it stops entirely? Understanding the elegant beauty of kinetic theory is really just the first step in unraveling the mysteries of the universe. Thanks for learning with me today.
Welcome to the Explainer. Today we're diving into something absolutely mind-blowing. We're going to explore the awe-inspiring power of classical physics, its amazing ability to find perfect order in absolute chaos, and the tiny, seemingly insignificant mathematical glitch that basically broke the entire system and changed our understanding of reality forever. But to really get started, we gotta ask a pretty profound question. How do we actually predict the behavior of a billion colliding atoms? You know, if we just look at the macroscopic world around us, the air we're breathing right now, the water we drink, it all seems incredibly stable and perfectly predictable. But let's zoom in. Down at the microscopic level, matter is really just a frantic, chaotic swarm of particles smashing into each other billions of times a second. So how on earth do we actually make sense of all that? Well, that brings us to our first section, the molecular point of view, focusing on kinetic theory. Kinetic theory asserts this brilliantly simple idea that the gross, visible properties of matter we interact with can be explained entirely through the invisible collisions of its countless tiny parts. Physicist Richard Feynman used a really elegant thought experiment to explain this, using an atmospheric column. Imagine a towering tube of gas. If the temperature were somehow hotter at the very bottom than at the top, we could connect a rod with balls on each end inside it. The fast-moving, hot molecules at the bottom would start violently shaking the lower balls. That kinetic energy would travel right up the rod, shaking the top balls, which would then heat up the molecules at the top. It's like a giant domino effect of energy. Ultimately, all those constant chaotic collisions guarantee that the temperature perfectly equalizes at all heights. Chaos literally creates absolute equilibrium. Okay, moving on to section 2, the exponential atmosphere, and taking a look at gravity's role. So what happens when we introduce a force we're all pretty familiar with, gravity, into this perfectly balanced atmosphere? Because gravity is constantly pulling everything down, the gas pressure has to be higher at the bottom just to support the sheer weight of the gas above it. And this means the density of the gas actively decreases as we go higher up. But different molecules drop off at different exponential rates. Oxygen is a lot heavier than hydrogen, right? So its density just plummets dramatically with height, while the much lighter hydrogen kind of stretches out way further into the upper atmosphere. Now, here's the crucial part. This isn't just some random accident caused by gravity. This brings us to a universal principle of statistical mechanics known as Boltzmann's law. It basically states that the probability of finding molecules in any specific spatial arrangement varies exponentially with a negative of its potential energy divided by the temperature, or kT. Whether we're talking about gravity, electric fields, or even molecules attracting each other to form liquids, atoms always arrange themselves based on this beautiful, predictable tug-of-war between their potential energy and their thermal heat. Right, let's look at section 3, a swarm of speeds, and talk about velocity distribution. So we've figured out roughly where these molecules are hanging out, but we really need to figure out how fast this swarm is actually moving. We established there are fewer molecules higher up, but wait, don't all molecules eventually bounce upward? Well, yeah, but gravity creates this invisible, vertical potential energy hill. A molecule literally has to pay a toll in kinetic energy to climb that hill. Only the absolute fastest moving molecules have the raw speed required to fight gravity and reach those higher altitudes. If you track the upward paths to these molecules, you'll see exactly what I mean. A molecule starting out might just not have enough vertical velocity. It shoots upward, completely runs out of kinetic energy, and falls tragically short. But a faster molecule, it has enough speed to push right through an upper plane at a specific height. Because the overall density of the gas drops exponentially as you go higher, this basically proves that the number of molecules with those super high velocities has to drop exponentially too.
Now, obviously, we can't just point to one single molecule in the real world and say, oh yeah, that one is going exactly 1.79 meters per second. That's impossible. But the amazing thing is, we don't even need to. This bell-like curve we get is the velocity distribution function. It perfectly predicts the exact fraction of all particles moving within any given range of speeds. The mathematical laws of probability have completely, thoroughly tamed the chaos.
Which brings us to a huge turning point. Section 4, the specific heat mystery, or where classical math completely fails.
Up until this exact point in history, 19th century physicists were feeling pretty incredibly confident. Classical statistical mechanics seemed practically magical in its ability to predict reality, until we hit this exact moment where the math just hits a brick wall. When we look at the experimental measurements for a value called gamma, which relates to the specific heat or internal energy of gases, things get weird. For a simple monatomic gas like helium, which is just single round atoms bouncing around, the measured gamma is 1.66. And hey, that matches the classical prediction perfectly. But then you look at hydrogen and oxygen. These are diatomic gases, meaning they're like two atoms connected together like a tiny dumbbell. Classical physics definitively predicts their gamma should be exactly 1.286, but the actual real-world measurements are around 1.40. The math just completely, undeniably fails. And honestly, the mystery deepens wildly when you start messing with the temperature. Classical theory absolutely insists that internal energy should be independent of temperature. That predicted value of 1.286 is supposed to be totally flat. But look at what actually happens with the experimental values for hydrogen and oxygen. The lines curve drastically. As the temperature drops, the gamma for hydrogen shoots way up, drifting even further and further away from the classical rules. You really have to put yourself in their shoes to understand the sheer despair this caused the scientific community. These physicists had rigorously, painfully proven their theorems. The math was flawless, yet it totally contradicted reality. It was so frustrating that in 1869, James Clerk Maxwell, who was literally one of the brilliant minds behind the theory, stated, "I have now put before you what I consider to be the greatest difficulty yet encountered by the molecular theory." They knew the whole framework was fundamentally flawed, but they had absolutely no idea why.
Enter the fix. Section 5, the quantum resolution, and the discovery of energy in discrete steps.
It actually took decades to figure this out. To fix this giant glitch, science needed a massive paradigm shift. Let's contrast how they used to look at things versus what's actually happening. The classical view assumed that a diatomic molecule, our little dumbbell, could vibrate smoothly at any continuous, infinite range of energy levels. But the quantum view came along and proved that energy levels only exist in discrete, measurable steps. Think of it like a staircase instead of a smooth ramp. Physicist James Jeans described this beautifully as a freeze-out. At very low temperatures, the molecule literally doesn't have enough heat energy to reach even the very first step on that staircase. So its vibration effectively freezes out of existence. It just stops. Basically, a molecule can only jump up to the next vibrating state if the thermal heat energy surrounding it is actually bigger than the quantum energy gap. Take a hydrogen atom, for instance. It's incredibly light, which means its natural frequency of vibration is super high. It takes a massive amount of heat just to jump that first quantum gap. So at room temperature, hydrogen just doesn't have the heat required to vibrate at all. It acts like a completely rigid object. Classical physics couldn't predict this because, well, classical physics didn't know the universe was quantized. So let's take a step back and summarize this incredible journey we've just been on. We saw how classical mechanics does this wonderful job predicting macroscopic properties by taming the absolute chaos of billions of atoms using probability. But then, this tiny, stubborn discrepancy in the specific heat of diatomic gases basically broke that entire classical framework. Quantum mechanics had to sweep in and fix it by proving that energy actually exists in discrete, locked steps. If it's too cold, entire modes of molecular movement simply freeze out of reality altogether. Which leaves us with a pretty provocative final thought. We look around every single day, and we see this stable, predictable, classical world. But if that solid reality is actually just an illusion, built on these strange, hidden, discrete quantum rules that literally freeze and unfreeze based on temperature, what other classical laws of our universe are just waiting to be broken? Thanks so much for joining me for this explainer. I really hope it sparked your curiosity to look at the world just a little bit differently.
Welcome back to The Explainer. Okay, today we're tackling something pretty mind-blowing.
We are going to connect the completely random microscopic jiggling of matter right to the birth of quantum mechanics, and even to that static noise you hear inside everyday electronics. It's an absolutely wild ride through the history of physics, so let's just jump right in. So I want to hook you with a little mystery to start us off. What does ancient trapped water have to do with quantum mechanics? Well, back in 1827, a botanist named Robert Brown was peering through his microscope, and he noticed plant pollen just jiggling around relentlessly in water. At first, he actually thought it was alive. But to test this out, he grabbed a piece of quartz rock with a tiny droplet of water trapped inside, water that had literally been sealed off for millions of years. He looked at the microscopic dirt inside that ancient water, and he saw the exact same relentless, never-ending motion.
Okay, let's dive into this. This bizarre phenomenon became known as the Brownian movement. It's the continuous, totally irregular jiggling of microscopic particles suspended in a fluid or a gas. But what's actually causing it? Well, it's caused by the unseen thermal motion of molecules. You see, the water itself isn't perfectly still. Its molecules are constantly vibrating and zipping around, continuously smashing into those suspended particles.
Part 1. The Jiggling Universe. To really wrap our heads around this, we have to establish the foundational rules of classical physics by looking at how energy is distributed when things reach what we call thermal equilibrium. A brilliant way to visualize this invisible force is the pushball analogy. Imagine looking down at a huge stadium from a helicopter. You see this massive ball moving around completely irregularly. You can't see the crowd underneath it, but you know people are pushing it randomly in all directions. That's exactly what's happening to a heavy microscopic particle. It's being heavily bombarded by invisible water molecules. And classical physics tells us that this particle, in thermal equilibrium, gains a very predictable mean kinetic energy, which is mathematically represented as 3/2 kT.
Part 2. Noise in the machine. We're going to shift from water to technology now, because as it turns out, this microscopic jiggling rule, it literally applies everywhere in the universe. Now, what's really interesting about this slide is that if you consider a highly sensitive laboratory instrument like a light beam galvanometer, it uses a tiny mirror suspended on a super delicate quartz fiber. But here's the thing, even if you build the most perfect, delicate mirror mathematically possible, it still won't stay perfectly put. It wobbles constantly. Why? Because it's being hit by gas molecules in the air. Its rotational kinetic energy is 1/2 kT. The universe physically won't let it sit still.
And this brilliant little concept crosses right over into our everyday electronics. Take a high Q resonant circuit. If you build a highly sensitive radio receiver, you're going to detect static noise. We call this Johnson noise. And it happens because the electrons inside the circuit's resistor are physically jiggling around due to thermal equilibrium. The ambient heat of the room makes the electrons vibrate, and that creates tiny random electrical fields.
Part 3. The classical catastrophe. This brings us to a massive historical problem. If every single oscillator, like every atom, every electron, shares energy equally based on temperature, what happens to light and radiation inside a perfectly hot box? Seriously, why doesn't an open furnace just burn our eyes out with X-rays? According to classical physics, an atom is a tiny oscillator, and as it jiggles, it emits light. The classical math predicted that as you go up in frequency, the oscillator should just keep taking on more and more energy. It mathematically guaranteed that any hot object, like a furnace, should emit an infinite amount of high-frequency energy, meaning you get an endless blast of deadly X-rays the second you open the door.
Notice the solid line on this graph shooting straight up into infinity? That is classical physics, specifically Rayleigh's law, predicting infinite X-rays. But see that dashed curve below it? That's actual reality. The light intensity peaks and then drops back down beautifully. So classical physics was fundamentally, powerfully, and absolutely wrong.
As the legendary physicist Richard Feynman so perfectly put it, thus was the classical theory absolutely incapable of correctly describing the distribution of light from a black body. The gravity of this crisis cannot be overstated here. The universe, at least according to human math, was broken. Scientists desperately needed a brand new paradigm to explain why reality wasn't matching their equations.
Part 4. The Quantum Oscillator. And this is where the ultimate plot twist in the history of science happens. A physicist named Max Planck steps up and proposes a radical, almost unthinkable new rule to fix that broken curve.
Planck introduced a really weird assumption about permitted energy levels. Before this, everybody just assumed energy was a smooth gradient. You could have any tiny fraction of energy you wanted. But Planck argued, what if energy isn't smooth? What if it can only be absorbed or emitted in discrete, strict mathematical steps? This bizarre idea was the spectacular beginning of the end for classical mechanics.
So the absolutely crucial point here is this. Classical physics says oscillators hold any energy, like a smooth ramp. Quantum physics says energy only exists in discrete steps, like a staircase. Why does this solve our furnace problem? Because high-frequency oscillators, the ones that would create those deadly X-rays, require a massive amount of energy just to reach their very first step. At normal temperatures, the thermal jiggling simply doesn't pack enough punch to reach that first quantum step. So they don't radiate at all. The high frequencies are essentially frozen out, perfectly matching that dashed reality curve we saw earlier.
Part 5, the random walk. Now let's bring all this esoteric quantum math right back down to the physical world by returning to our jiggling Brownian particle floating in water.
To figure out the totally unpredictable path of our particle, we have to use the drunken sailor analogy. Imagine a sailor stumbling out of a bar, taking random steps in arbitrary directions. If our microscopic particle is getting randomly hit by water molecules 10 to the 14th power times every single second, where does it actually end up after a given amount of time?
Let's move to the logic and see how this builds. First off, every step is random and totally unrelated to the last one. Second, by adding the vectors, we find the mean squared distance. And third, the massive revelation. The mean squared distance grows proportionally with time, not velocity. The drunken sailor isn't moving away with uniform speed. Rather, the square of his distance from the bar strictly follows the ticking of the clock.
The power of this mathematical jiggle is just astounding. It determined the exact distance a particle drifts over time and measured irreversible fluid drag. In 1905, Albert Einstein used this exact math of chaotic jiggling to calculate Boltzmann's constant, which finally allowed him to solve Avogadro's number. This definitively proved the physical size and quantity of atoms in a given mass, permanently grounding our entire modern understanding of matter.
So I want to leave you with this final, provocative thought. If all matter at its very core is just a random walk of vibrating atoms, how predictable is our universe really? It's pretty marvel-inducing to think that a tiny piece of dirt jiggling under a microscope back in 1827 eventually broke classical physics, mapped the size of the atom, and revealed the invisible quantum rules that govern our entire reality. Thanks for joining me on this explainer. Keep asking questions, and I'll catch you next time.
Welcome to The Explainer. So, have you ever wondered if there's just one single, beautiful mathematical thread tying the entire chaotic, microscopic universe together? Well, today, we're actually going to find it. We're diving straight into a foundational principle of kinetic theory, one that literally dictates how particles behave across some wildly different environments. I mean, think about it for a second. What do a drying puddle, a vintage radio tube, the freezing cold void of interstellar space, and a highly focused laser pointer all have in common? It kind of sounds like the setup to a weird joke, right? But the answer is honestly profound. Every single one of them relies on the exact same microscopic mechanism. It's basically this chaotic game of chance played by atoms and electrons. Okay, so here's our game plan for The Explainer today. We're going to look at 1. The rule of borrowed energy. 2. Electrons escaping hot metal. 3. Ions in the cold void. 4. Climbing chemical energy hills. And finally, 5. Einstein, light, and lasers. Let's jump right into this structured path through the particle universe and find that unifying thread. Kicking things off with Section 1, the rule of borrowed energy. To really wrap our heads around the grandest technologies, we actually need to look down at the sidewalk after a rainstorm. Let's ground this physics in something super relatable, a simple puddle of water evaporating. Now, evaporation isn't this smooth, steady thing. It's actually a microscopic lottery for individual molecules. Inside the liquid, water molecules are packed tightly together, held by attractive forces. To evaporate, a single molecule has to completely break those bonds. It needs extra energy, a specific amount of work we'll call W, just to pull away. But here's the catch. The average energy of a molecule just isn't enough. It literally has to win the lottery by randomly bumping into its neighbors and borrowing enough excess energy to escape. And as Richard Feynman famously pointed out, the probability of finding a particle in different places varies as e to the minus potential energy over kT. Okay, I know that sounds like a bit of a mouthful, but simply put, this exponential rule represents the steepness of the energy hill a particle has to climb to break free. And because it's an exponential relationship, even a tiny change in temperature, that T in the equation, drastically alters the odds of a molecule having enough energy to escape. This is exactly why hot water evaporates so much faster than cold water. It's all about the odds. Moving right along to Section 2, electrons escaping hot metal. So we've seen how this plays out with water. Now let's transition to technology and look at thermionic emission, the exact science that powered vintage radio tubes and early electronics. Picture a piece of metal, like a tungsten filament inside a vacuum tube. Just like water molecules are bound to a puddle, electrons are tightly bound to that metal. Apply heat, and they start jiggling faster. Every so often, an electron gets bumped hard enough to grab the excess energy it needs to jump right off the surface. It essentially boils off, giving us a flow of electrons that we can actually use to carry electrical signals. But we really need to understand the sheer amount of energy we're talking about here. It takes roughly 1 electron volt of work to pull an electron off a typical metal surface. Now, to put that into perspective, 1 electron volt corresponds to the average thermal energy of a staggering 11,600 degrees. But a radio tube filament only operates around, say, 1,100 degrees. So the vast majority of electrons don't have anywhere close to enough energy. Only the incredibly rare, absolutely lucky winners of that microscopic energy lottery ever escape, dictated perfectly by our exponential rule of borrowed energy. Next up, Section 3, Ions in the Cold Void. Let's completely shift our scale here, from blazing hot radio tubes to the freezing, vast expanse of interstellar space. How does our energy rule apply when there's almost no heat at all? Well, whether we're talking about water, metal, space, or chemistry, it is always the exact same story. You have escapers trying to break a bond. In thermal ionization, for example, the escaper is just an electron trying to break free from a single atom, which then turns that atom into an ion. And here is where things get truly weird. Pulling an electron entirely out of an atom takes a massive amount of energy, way more than the average thermal energy floating around in the freezing void between the stars. The odds of an electron borrowing enough energy to escape out there are just astronomically low. So why do we find so many ions in deep space? Well, it's because space is just so incredibly vast. If an atom does somehow get pinged by a stray ray of light and loses an electron, that electron wanders off into the enormous void. It might take years for it to randomly bump into another ion and recombine. The rate of escaping is microscopic, sure, but the rate of returning is basically 0. Let's take a look at Section 4, Climbing Chemical Energy Hills. So how does this build into the very chemical reactions that make life possible? Imagine 2 molecules, A and B. They want to combine to form compound AB. Now, even if forming AB releases energy overall, dropping them into a nice, deep energy valley, they can't just lightly tap each other to react. No, they have to hit each other hard. They first have to borrow enough extra energy to climb that initial hurdle, the activation energy, which we call A star. And once again, the exact same mathematical law governs the probability of them hitting each other hard enough to crest that hill. This actually perfectly explains an absolutely crucial concept in chemistry, catalysts. See, a catalyst doesn't magically alter the starting energy of the molecules, and it doesn't change the final energy of the product either. It just hacks the probability. It physically provides a different path, maybe offering a lower hill to climb, or even creating a sort of tunnel street through it. By slightly lowering that activation energy, the exponential math swings wildly in our favor. So a reaction that might naturally take years can suddenly happen in seconds. Pretty wild, right? And that brings us to our final section, number 5, Einstein, Lights and Lasers. We have officially reached the climax of our explainer. This is where we take this statistical jiggling and apply it to light and matter itself. It's where we go from just understanding nature to actively engineering it. Let's walk through a brilliant realization Albert Einstein had back in 1916. He was studying how atoms transition between energy levels, absorbing and emitting photons. Everyone already knew about absorption. An atom eats a photon and jumps to a higher energy state. And everyone knew about spontaneous emission. An excited atom eventually drops back down and just randomly spits out a photon. But Einstein realized the math actually required a third process to balance everything out. He called it induced or stimulated emission. He figured out that if an atom is already excited, a passing photon of the exact right frequency can actually force that atom to drop its energy instantly, emitting a second, perfectly identical photon in the exact same direction. Now contrast the normal equilibrium on the left with a clever trick on the right. In normal equilibrium, most atoms are just sitting peacefully in their lowest energy state. Shine light on them, they absorb it, simple. But what if we use a non-thermal method, like flashing a super bright light to pump the atoms up to a higher level? They trickle down and basically get stuck in this middle level, which we call a metastable state.
We've now created a completely unnatural situation. We have tons of excited atoms, all just waiting to drop. And that is when we spring the trap. A single photon triggers one atom to drop, releasing a second photon. Those two hit two more atoms, releasing 4, then 8. Boom! We've created an explosive chain reaction of induced emissions. Trap this whole process inside a box with near-perfect mirrors on both ends, and those photons just bounce back and forth, sweeping through the atoms over and over, dumping all their energy at once. A tiny sliver of that massive, coordinated wave of identical photons escapes through one mirror, and just like that, a laser is born. I want to leave you with this final, provocative thought. We started with the chaotic, random, totally unpredictable jiggling of molecules in a drying puddle, a literal statistical game of chance. But by understanding the strict mathematical rules behind that chaos, we figured out how to stack the deck. We engineered a way to take that chaotic lottery and turn it into the most precise, perfectly synchronized, directional beams of light in the known universe. That is the unbelievable power of kinetic theory. Thanks so much for joining me for this explainer, and remember to always keep questioning the universe around you. Hey everyone, and welcome to the Explainer. Today, we're taking a seriously fascinating journey straight into the mind of the legendary physicist Richard Feynman. Have you ever actually stopped to wonder how the total chaos of billions of tiny molecules just bouncing around and smashing into each other at absolutely breakneck speeds somehow results in the perfectly predictable, everyday stuff we see around us? I mean, think about it. How does electricity flow so reliably through a wire? Or how does the smell of fresh coffee spread so smoothly across a room? Well, today, we are going to demystify the physics of diffusion. We'll be bridging that crazy gap between the frantic, microscopic physics of non-equilibrium states and the macroscopic world that we can actually see, feel, and measure. Let's get into it. Okay, let's dive into this. Here is our mental roadmap for the micro to macro journey. We're going to start with basic molecular collisions, then introduce drift speed. From there, we scale up to ionic conductivity, look at molecular diffusion, connect the dots with a brilliant historical insight, and finally wrap the whole shebang up with thermal conductivity. Starting off with Part 1, Molecular Collisions and Free Paths, the chaotic baseline. So, to really understand what happens when a gas is pushed out of balance into a non-equilibrium state, we first need to understand the baseline rules of thermal equilibrium. On the left side here, we've got thermal equilibrium. Inside that gas, everything is just purely random. There's zero net flow in any direction. Broad statistical mechanics and classical thermodynamics handle this beautifully. But look on the right. In non-equilibrium, like imagine we suddenly apply an external electric force or a gravitational pull, the entire system shifts. We can't just rely on those broad, static thermodynamic averages anymore. We actually have to step into kinetic theory and analyze what occurs atom by atom as these particles fight their way through the invisible crowd. And to do that effectively, we need a basic ruler to measure this microscopic chaos, right? So we use a really critical concept, the mean free path, which is represented by the lowercase letter L. This is literally just the average distance a molecule manages to travel before it smashes into another molecule. We calculate this by multiplying tau, which represents the average time between collisions, by v, the molecule's velocity. Now, it's absolutely crucial to remember that this tau is precisely that, an average. In reality, a molecule doesn't just have a collision, wait exactly 1 microsecond, and then perfectly schedule another one. No way. The actual times between individual hits vary wildly, but statistically speaking, tau gives us a highly reliable baseline to work with. And this brilliantly illustrates what we're talking about. Imagine our single particles shooting horizontally through a box full of background molecules. How far it actually gets, its free path, depends entirely on how big of a target those background molecules represent. We call this effective target size the collision cross-section. You can kind of think of it as a rigid area around each scatterer. If this cross-section is large, or if the background gas is incredibly dense, our moving particle isn't going to get very far at all before a collision. It's essentially playing a relentless microscopic game of dodgeball. Moving on to Part 2. Drift speed and mobility, the stop-and-go nudge. Okay, so now that we've got a handle on basic collisions, what happens if we give a quote-unquote special molecule a specific push? Imagine we apply an electrical force to a charged ion. Step 1, it accelerates due to that force, picking up real speed in a specific direction. But then, step 2,
Bam! It collides with a background molecule. Step 3. It completely loses that forward momentum and gets scattered in a totally random direction. It essentially gets a fresh start with zero memory of its previous path. And then, step 4. The cycle repeats itself. The molecule darts hither and yon, bouncing around completely randomly. But because of that constant force acting on it during its brief free times, it makes a slow, net progress in the direction of the force. And that right there is what we call drift. So, the absolutely critical point here is figuring out how to quantify this drift. This brings us to mobility, represented by the Greek letter mu. Mobility is simply the ratio of that drift velocity to the applied force. As you can see, it's calculated as the average time between collisions, tau, divided by the mass of the molecule, m. Now, here is a fascinating trap that even a ton of physics textbooks fall right into. If you assume every single collision happens at exactly the average time tau, and you just use a simple averaging formula of final velocity divided by 2, you actually get the wrong answer. Why? Well, because short free times happen way more often, but they contribute very little to the final speed. Long free times happen less often, but they allow the molecule to really accelerate and get going. Feynman specifically warns us about this. The correct average actually relies on the full distribution of these wildly varying free times. That lands us at this simple formula. Mu equals tau divided by m, completely dodging that erroneous 1/2 factor.
Let's move to and see how this builds in part 3. Ionic conductivity and current, scaling up to electricity.
All right, we're finally ready to apply our physics to a macroscopic container. In this schematic, we have a gas filled with special charged ions, and they're sitting between two metallic plates connected to a battery. By turning on that battery, we apply a voltage, which creates a uniform electric field pointing straight across the gas. Instantly, all those little ions feel that force. They start doing their stop-and-go microscopic dance we just talked about, slowly drifting toward the plates. This collective, coordinated drift of charged particles across the space is exactly what we call an induced electric current. Our gas is essentially acting like a giant invisible resistor. And here is where a really profound connection emerges. By calculating the total charge of these drifting ions arriving at the plate over time, we find mathematically that the total electric current is directly proportional to the applied voltage. Does that sound familiar? Because that's Ohm's law. We didn't just accept Ohm's law as some given textbook rule, we literally just built it completely from the ground up, using nothing but the chaotic bumping of individual molecules. The macroscopic resistance of this gas is perfectly derived from its microscopic properties, the number of ions, their individual electric charge, and their mobility. It's just a beautiful, solid bridge from the invisible atomic world right into the measurable, everyday world. Which brings us to part 4, the mathematics of molecular diffusion, spreading out. Let's pivot for a second to a totally different scenario. Let's turn off all the electric fields and external forces. If we inject a puff of a special gas into one corner of our room, even with zero wind currents, we know it eventually spreads out, right? Well, it spreads entirely because of random molecular collisions. We measure this with a new metric called the diffusion coefficient, represented by D. This measures the rate of spread based on the density gradient. Now, a highly crucial concept to grasp here is that net flow only happens when there is a non-uniform distribution of molecules. If a gas is perfectly mixed everywhere, the molecules are still moving randomly, sure, but the number going left exactly equals the number going right, meaning zero net flow. But if there's a dense, concentrated cloud of our special gas on the left, statistically speaking, far more molecules will randomly wander to the right than to the left. So the net flow of special molecules is directly proportional to the gradient of the density, and mathematically tied right back to our old friends, the mean free path and the velocity of the molecules.
Let's dive into part 5, connecting diffusion and mobility, the Einstein relation.
Now, what's really interesting about the slide is we are about to connect that electric drift we saw earlier with the random gas diffusion we just covered, and we're doing it in a truly historical way. Notice this direct quote: "Mobility and diffusion are intimately connected. This relation was first deduced by Einstein." Both of these concepts rely fundamentally on thermal motions and the mean free path of the molecules. By substituting our molecular definitions into the math, we find that the diffusion coefficient, D, is exactly equal to the mobility, mu, multiplied by Boltzmann's constant K and the temperature T. This is the famous Einstein relation. It inextricably links how fast a particle drifts under an external force to how fast it randomly diffuses when left completely alone. How cool is that? To prove this wasn't just some mathematical fluke, Feynman walks us through an incredibly elegant thought experiment. Imagine a gas diffusing, creating a flow or current. Now imagine artificially applying an opposing force, Maybe like gravity or a perfectly tailored electric field that pushes the molecules back exactly as fast as they try to diffuse forward. We create a perfect balance where the drift current perfectly cancels out the diffusion current. Because this puts the whole system into a stable equilibrium condition, we can suddenly apply the strict, irrefutable laws of statistical mechanics. And when we do the exact math for that perfect balance, we derive the exact same equation, D equals mu times KT. This proves that the Einstein relation holds true universally, and it's completely robust even in complex situations like liquid suspensions where our simple gas assumptions would normally fail. Finally, Part 6, Thermal Conductivity in Gases, Heat in Motion.
So how does heat actually move through a gas if there are absolutely zero convection currents blowing it around? Well, it turns out it's really just diffusion all over again. The hot, highly energetic molecules diffuse downward into the cooler regions, while the cold, slower molecules diffuse upward. When we mathematically calculate the thermal conductivity, or kappa, we're basically looking at the rate at which thermal energy is carried across an area. And the algebra here reveals something incredibly counterintuitive. The conductivity naturally relies on the average velocity of the molecules, which directly depends on the temperature, and their size, meaning their collision cross-section. But if you look closely at the underlying equation, the density of the gas itself completely cancels out.
Which leaves us with this final, highly counterintuitive question to ponder. Why is the rate of heat conduction in a gas completely independent of its density? I mean, you'd naturally think a thinner, less dense gas would be much worse at conducting heat, right? But the elegance of kinetic theory gives us the exact answer. If you drop the density of the gas, yes, you absolutely have fewer molecular carriers available to transport that heat energy. But at the exact same time, because the gas is less dense, the mean free path of those remaining molecules dramatically increases. Those fewer carriers can suddenly travel much farther distances between those energy-sapping collisions. So the drop in the raw number of carriers is perfectly mathematically compensated for by the increased distance they can travel. And just like that, the microscopic chaos perfectly balances itself out to dictate the grand, macroscopic rules of our universe. It truly makes you wonder, what other everyday, solid rules of life are really just the statistical averages of billions of tiny, invisible collisions? Keep questioning the world around you. Keep learning. And hey, thanks for exploring this amazing topic with us today. Welcome to This Explainer. Today, we're diving straight into the fundamental laws of the universe. We're going to step logically from the surprisingly weird behavior of a simple rubber band all the way to the grand abstract concept of entropy. It's a fascinating journey, and it really proves just how much we can deduce about reality without even needing to know all the microscopic details. Here is our quick roadmap for today. We'll start with a rubber band engine, move through the first and second laws, look at reversible engines, tackle the ultimate efficiency limit, and finally, we'll wrap up by understanding entropy.
All right, part 1, the rubber band engine.
So can you actually power a wheel with just rubber bands and a heat source? To figure that out, we have to look at the tangled molecular spaghetti that makes up a rubber band. If you stretch a rubber band and quickly place it against your lips, you'll actually feel it get warm, and when you let it relax, it cools down. Now, our everyday instincts might tell us that heating something makes it expand, right? But if you hang a weight on a stretched rubber band and hit it with a flame, it actually contracts. Why? Well, rubber is made of these long, tangled chains of molecules. When you pull it, the chains line up nicely, but when you heat it, the thermal agitation makes all those molecules pound into each other from the sides. That causes the chains to kink up and pull inward. So if heating a stretched rubber band makes it contract, we really have to ask ourselves, can we harness that heat to do actual physical work? Well, take a look at this incredibly silly bicycle wheel engine. Instead of standard metal spokes, it uses rubber bands. If you set up heat lamps to blast the bands on just one side of the wheel, those bands become stronger and contract. This literally pulls the center of gravity of the wheel off-center, causing the whole thing to turn. As it rotates, cool bands move into the hot zone, and the hot bands move away and cool down. It absolutely proves that by applying heat to one side, we can shift the center of gravity and do work with heat. But of course, there's a huge catch here. This engine is terribly inefficient. To figure out how to build a better one, we need the heavy-hitting science of thermodynamics.
Which brings us to part 2, the first law of thermodynamics.
If we're going to build better engines, we absolutely need to nail down the conservation of energy. The crucial point here is that energy doesn't just disappear into the ether. Any heat you add or any work you do is strictly accounted for in the system's total internal energy. You simply can't get something for nothing. If you pump heat in and do work on the system, its internal energy goes up by exactly that combined amount. And this diagram brilliantly captures the basic heat engine concept. You're taking heat from a boiler at a high temperature, using a chunk of it to do some useful work, and then exhausting whatever is left over into a condenser at a lower temperature. The legendary engineer Sadi Carnot actually started analyzing engines just like this before the first law was even totally established. But armed with the first law, we know for a fact that the heat exhausted is exactly equal to the heat put in minus the work done. Moving right along to part 3, the second law. Now, you might be wondering, why can't we just ditch the condenser and extract massive amounts of free energy straight from the ocean? The ocean has plenty of thermal energy, right? Well, Carnot realized there's a fundamental roadblock. You absolutely cannot extract heat from a single temperature source to do work without leaving some kind of footprint or making other changes to your surroundings. Think about it. If you could, you'd extract heat from the ocean, use it to do work, and then convert that work back into heat via friction to warm up something else. You'd essentially be making heat flow from a cold ocean to a hot object for absolutely free. And our everyday experience tells us heat naturally flows from hot to cold, never the other way around. So to push an engine to its theoretical maximum efficiency, we have to eliminate friction completely. And the thermal equivalent of frictionless motion is a perfectly reversible heat transfer between nearly identical temperatures. Look, if you slap a hot object against a cold object, heat flows one way and it's totally irreversible. But if the two objects are sitting at essentially the exact same temperature, with only an infinitesimal difference between them, you can reverse the direction of the heat flow with just a tiny adjustment. That right there is the secret sauce for the ultimate ideal engine. This sets us up perfectly for part 4, reversible engines and the Carnot cycle. Picture a cylinder of perfect gas, equipped with a frictionless piston. We can break this flawless cycle into 4 very clean steps. First, expanding the gas while adding heat to keep it at a constant high temperature. That's isothermal. Second, expanding it even further without letting any heat in or out, so the temperature drops. That's adiabatic. Third, compressing it while removing heat at a constant low temperature. And finally, compressing it right back to the start without letting any heat transfer at all. When you map this out on a pressure volume diagram, it looks like this. That shaded area inside those 4 curves, that literally represents the useful network our ideal gas has done for us during one single cycle. And because every single step is perfectly reversible, we could actually run this exact engine backward. If we run it in reverse, we do work on the gas, and it pumps heat from the cold reservoir straight up into the hot reservoir. This flawless reversibility is the core of Carnot's genius. Let's jump into part 5, the ultimate efficiency limit. Okay, we are going to set a brilliant logical trap here to prove that literally no engine in the universe can beat that reversible Carnot cycle. Let's imagine some newly invented engine B that claims to be highly efficient, more efficient than our reversible engine A. If that were true, we could theoretically take engine B's extra work and use it to drive engine A backwards. Let's say they both pull the exact same amount of heat from the hot boiler. Engine B supposedly does more work, right? So we siphon off part of B's work to run engine A in reverse, pumping that exact same amount of heat perfectly back into the hot boiler. But here is why that is a total bust. This thought experiment proves that if engine B were actually more efficient, our combined supermachine would be extracting net work solely from a cold reservoir, which the universe strictly forbids. The hot boiler is completely unaffected because engine A put back the exact amount of heat engine B took out. So the net result is that we're doing useful work just by sucking heat out of the cold condenser. Since the second law loudly states that's impossible, engine B simply cannot be more efficient than engine A. End of story. Because all perfectly reversible engines must be equally efficient, we can do something really amazing. We can define an absolute temperature scale based purely on how much heat these ideal engines absorb, regardless of what material they're actually made of. Whether your engine runs on steam, a perfect gas, or those weird molecular spaghetti rubber bands, the efficiency is a universal property of nature, not the substance itself. We just measure the heat absorbed at one temperature versus a standard 1-degree baseline to define our absolute thermodynamic scale. Just look at this elegant little formula. It shows that your efficiency depends entirely on the gap between the hot and cold temperatures. This proves mathematically that 100% efficiency is physically impossible unless your cold reservoir is sitting all the way down at absolute zero. The wider the gap between your hot boiler and your cold condenser, the more efficient your engine is going to be. But perfection, it's always just out of reach. And that brings us to our grand finale, part 6,
understanding entropy. This whole logical journey leads us to a profound new property of state. Whenever our ideal engine moves heat around, the ratio of that heat to the temperature is a strictly conserved quantity. We call it entropy. In a perfectly reversible cycle, the amount of heat absorbed divided by the high temperature perfectly matches the amount of heat delivered divided by the low temperature. There is no net gain and no net loss of this ratio. If we chart a reversible transformation along any crazy path on our graph, the total change in entropy is simply the sum of all those 20 little heat transfers divided by their specific temperatures. Imagine shifting a gas through all kinds of different pressures and volumes, connecting it to a series of tiny heat reservoirs along the way. The total entropy delivered is mathematically rigorous, and it depends strictly on where you start and where you end. And as this brilliantly illustrates, if you complete a perfectly reversible cycle and end up exactly where you started, your net change in entropy for the entire system is exactly zero. Because the entropy change is totally independent of the path you take, going out one way and coming back another puts you right back at baseline. Entropy, therefore, is a definitive property of the state of a substance, exactly like its pressure or its volume. But let's be real for a second. In the actual, messy world, friction and the natural flow of heat from hot to cold guarantee that actual processes are irreversible. And because they're irreversible, they always generate a positive increase in entropy. A perfectly reversible process is just a useful idealization. When you generate heat through friction or drop a hot stone into a bucket of cold water, the entropy lost by the hot object is always slightly less than the entropy gained by the cold one. The math simply guarantees it. As we wrap up this explainer, we are left with this profound, inescapable truth about the universe, summed up perfectly by Richard Feynman. Every single natural action you take irreversibly increases the total entropy of the whole world. So the next time you carelessly stretch and snap a rubber band, remember, you aren't just messing around with tangled molecular spaghetti. You are permanently, irreversibly changing the thermodynamic balance of the entire universe. Which leaves us with a pretty heavy question. If every single action inexorably increases the universe's entropy, what exactly happens when it runs out of room to grow?
Welcome. I'm so incredibly excited to jump into this explainer with you today because we're tackling a subject that honestly strikes fear into the hearts of a lot of students, thermodynamics. But I'm here to tell you right off the bat that thermodynamics is not just some dense, impenetrable jungle of partial derivatives and terrifying math. It's actually a universal translator for physical reality. It's a master key that lets us decode exactly how energy moves and transforms. And it does this without us needing to know every tiny little detail about the atoms and molecules involved. It's elegant, it's incredibly powerful, and by the end of this explainer, you're going to see the physical world in a completely different light.
To get us there, we've got a pretty straightforward roadmap today. First, we're going to brave the thermodynamic jungle. Second, we'll forge our master equation. Third, we'll apply it to rubber bands and batteries. Fourth, boiling liquids and vapor. And finally, we'll look at the sheer power of thermodynamics.
So, let me hook you right out of the gate with a little puzzle. What do a stretching rubber band, a standard car battery, and a boiling pot of water all have in common? I mean, on the surface, absolutely nothing, right? They run on completely different mechanical and chemical principles. But, as we're going to see, there is actually a single mathematical master key that unlocks the mysteries of all three.
All right, Section 1, the thermodynamic jungle, a maze of variables.
You know, the reason thermodynamics gets so famously complicated so fast is just the sheer number of ways you can describe the exact same thing. You've got pressure, volume, temperature, internal energy, entropy. It really is a literal jungle. So, to survive it, we have to be strict and limit our tools. For this explainer, we're putting our blinders on and using just two independent variables, temperature, which we'll call T, and volume, or V. We're going to look exclusively at how internal energy and pressure depend on just those two things. And honestly, doing this turns what feels like an impossible subject into a totally manageable logic puzzle.
Moving on to Section 2, the master equation, forging our main tool.
Okay, let's dive into this. This is kind of the eat your vegetables part of the explainer. But I promise you, if we use just a tiny bit of basic geometry, we're going to forge a tool of immense power. Take a look at this pressure-volume diagram for a Carnot cycle, which is basically a theoretical engine. Those curves marked with a T, those are isothermal lines, meaning the temperature stays completely constant. And the steeper lines are adiabatic, meaning no heat is sneaking in or out. As a gas expands and compresses to trace out this shape, the total net work done by that gas is represented exactly by the shaded area right there inside the cycle.
Now here's where it gets really cool.
If we make the changes in temperature and heat infinitesimally small, we completely avoid messy calculus. Richard Feynman brilliantly simplifies this by pointing out that the shaded shape basically just becomes a simple parallelogram. And geometrically speaking, the area of that parallelogram is just the change in volume, delta V, multiplied by the change in pressure, delta P. It's really that simple. This observation right here connects the mechanical work done to the heat added and the temperature change. It builds our absolute fundamental equation, linking pressure, volume, and temperature.
So what does this all actually mean? Well, this gives us our profound philosophical takeaway. Look at this quote from the source. Without knowing the internal mechanism, we can deduce the relationship between the amount of heat needed and the pressure change. Think about that. We do not need to know how individual atoms are bouncing around. We don't even need kinetic theory. Because we know perpetual motion is literally impossible, these macroscopic properties are locked into this intricate mathematical dance. Thermodynamics just hands us the exact answers, straight from the top down.
All right, let's hit Section 3, Rubber Bands and Batteries, Real-World Applications.
Now, what's really interesting about this is taking our newly forged master equation out of that theoretical gas cylinder and throwing it into the real world. This is basically the ultimate cheat code of physics. For a gas, work is pressure times the change in volume. But check out these substitutions. For a rubber band, work is force times the change in length. And for a battery, it's voltage times the change in charge. Since the structure of the math is perfectly identical, we can just swap the letters. Meaning, the exact same equations that run a massive steam engine perfectly explain why a stretched rubber band actually gets hot, or why your phone battery gets warm when you're charging it. It is literally the exact same underlying logic. How wild is that?
But, okay, there is a slight catch when we try talking to our friends over in the chemistry department. You see, physicists, they absolutely love temperature and volume. But chemists, well, they're generally working with open test tubes in a lab, right? And trying to hold volume constant in an open beaker is an absolute nightmare. So naturally, chemists rebelled. They much prefer equations that describe performance under constant atmospheric pressure rather than constant volume.
So, to keep the chemists happy, someone invented a really clever mathematical trick. Basically, by taking the internal energy, U, and adding the product of pressure and volume to it, we get a brand new function called enthalpy. We call it H. And enthalpy is quite literally just an algebraic workaround so chemists can use temperature and pressure as their independent variables without somehow breaking the laws of thermodynamics. It is the exact same physics, it's just wearing a different mathematical hat.
Moving along to Section 4, Boiling Liquids and Vapor, Phase Changes.
And this brilliantly illustrates what happens when we apply our thermodynamic tool to something a bit more volatile, like turning a liquid into a gas. If you look at the cylinder of liquid charted on the left, as you pull the piston out, the pressure drops until the liquid actually starts to boil. But then, check out that flat horizontal line. As you keep expanding the volume, the liquid just turns to vapor, but the pressure doesn't change at all. It stays exactly at the vapor pressure. Now, over on the right, we draw our Carnot cycle using that flat line. And by equating the heat needed to vaporize the liquid to the geometric area of that skinny little rectangle, thermodynamics effortlessly hands us the Clausius-Clapeyron equation. It perfectly links the heat of vaporization to how vapor pressure changes with temperature.
This whole thing perfectly highlights the ongoing battle between thermodynamics and kinetic theory. See, thermodynamics is universally exact. It applies to melting solids just as flawlessly as it does to boiling liquids. It really doesn't care if you don't fully understand the molecular bonds. But the catch is, it only gives us differential relationships. Now, kinetic theory, on the other hand, actually tries to model the atoms themselves bouncing around, which means it's often an approximation. And it can totally fail if the model is even slightly off. But when kinetic theory actually works, it's amazing because it gives us the constants of integration that thermodynamics leaves out. They really are two halves of the same incredibly powerful whole.
Finally, we arrive at Section 5, the power of thermodynamics, cosmic limits.
Let's move to and see how this builds when we take our master key completely out of the laboratory and point it right at the stars themselves. Imagine a box that isn't filled with gas, but is filled purely with radiation, just light photons. Now, we know photons exert a physical pressure. If we plug the energy and pressure of those photons into our exact thermodynamic equations, we discover a fundamental law of the universe. The pressure and the energy density of radiation scales exactly to the fourth power of the temperature, T to the fourth. Meaning, if you just double the temperature, the radiation energy goes up by a massive factor of 16. No way around it.
But, remember what we said earlier? Thermodynamics can't give us the constant of integration. To figure out exactly how much energy is radiating, we have to bring in kinetic theory, specifically the quantum intensity distribution of photons. And when we married those exact macroscopic rules of thermodynamics with the gritty quantum details, we solve the integral and unlock a true, fundamental number of reality, the Stefan-Boltzmann constant. That's 5.67 times 10 to the negative 8th watts per square meter per degree to the fourth. It is literally a perfect marriage of top-down thermodynamics and bottom-up quantum mechanics.
So thermodynamics lets us map the absolute limits of nature, from the scale of a tiny little rubber band all the way up to the blazing surface of a star, entirely through the logic of macroscopic observation. It guarantees that the universe makes sense, even when the microscopic details are completely hidden from our view. So I want to leave you with this to ponder. If thermodynamics can map the universe with such terrifying exactness, without us even needing to know its inner mechanisms, what other invisible, undeniable laws are out there secretly shaping the boundaries of our reality? Definitely something to think about next time you boil a pot of water. Thank you so much for joining me in this explainer, and keep that curiosity burning.
Welcome to the Explainer. I'm absolutely thrilled you're here today because, well, we're going on quite the journey. We're going to start by looking at a tiny, incredibly simple mechanical gear. And by the time we wrap up, we'll be using that exact same gear to explain the birth of the cosmos and the literal flow of time itself. It's a massive conceptual leap, for sure, but I promise we'll take it one logical step at a time. Before we even get to that gear, though, I want you to chew on a bit of a paradox. If the fundamental laws of physics work the exact same way forward and backward, and mathematically speaking, they totally do, then why can't you unscramble an egg? Right? Why does a dropped coffee mug shatter, but those shards never, spontaneously jump back up onto the table and perfectly reform? Just keep that in the back of your mind. To solve it, we really need to look at a machine.
Okay, let's dive into this. Section 1, the perpetual motion paradox. Now just look at the sheer simplicity of this device. This is the famous Ratchet and pawl machine, dreamed up by the legendary physicist Richard Feynman. Picture a box of gas at a certain temperature, and inside that box, you've got some flat vanes attached to an axle. That axle connects to a wheel on the outside. Notice the shape of that wheel. It's got these angled teeth. That is your ratchet. And resting right on top of those teeth is a little lever, which we call a pawl. So here's how this little contraption is supposedly meant to work at first glance. Step 1. The gas molecules inside the box are just bouncing around randomly because of their heat, continuously bombarding those vanes. Step 2. All that microscopic ping-pong causes the axle to jiggle back and forth. Step 3. The ratchet and pawl kick in, only allowing the wheel to turn in one single direction. When it jiggles one way, the pawl catches. When it jiggles the other way, it slips right over the angled tooth. And step 4. The wheel slowly turns. You could theoretically wind up a string and, as Feynman himself joked, lift a flea. I mean, it really seems like we've just harvested free energy straight from the random heat of a room. Sounds absolutely perfect, doesn't it? But, well, nature doesn't give away free lunches. Section 2, why the ratchet fails. The big problem here is that we're completely ignoring the physical, mechanical realities of the device itself. First off, that pawl needs a spring to push it back down onto the teeth. When it snaps down, if it's perfectly bouncy and elastic, it's just going to wildly bounce around, right? And that lets the wheel slip backward. So it needs some kind of damping mechanism to stop the bouncing. But here's the catch. Damping absorbs energy, and that energy turns directly into heat. As this machine runs, the wheel and the pawl get hotter and hotter. Eventually, the pawl gets so hot that it starts experiencing its own random thermal jitters, its own Brownian motion. It randomly bounces up completely on its own, right when the wheel is trying to turn backward, and boom, the wheel slips. The net result? Zero forward motion. None. And this brilliantly illustrates what happens if we actually want the machine to work. The vanes simply must be hotter than the ratchet itself. Notice how incredibly lopsided, how unsymmetrical this curve is? When the machine goes forward, borrowing energy from a hotter source, it's super easy. We get a whole lot of speed for just a little force. But trying to go backward against the heat, man, you can apply a massive amount of force and that wheel will barely even budge. If we break down the math on why that happens, it all comes down to a very delicate balance of energy. To take one step forward, the machine needs enough energy to lift the pawl plus the energy to actually turn the wheel against whatever tiny weight it's pulling. It borrows that extra kick from the hot vanes. But to slip backward, it only needs the energy to lift the pawl, which it happily just takes from its own heat. If the temperatures are exactly equal, the probabilities of going forward and backward perfectly cancel each other out. You get absolutely zero work done. Which leads us directly to a profound question about mechanics and time. Section 3, the reversibility problem. I absolutely love this quote from the text. It asks, are all the laws of physics reversible? Evidently not. Just try to unscramble an egg. It's such a punchy, perfect way to highlight the massive disconnect between neat mathematical theories and the messy, one-way reality of our actual lives. Because here is the core tension we're dealing with. On a microscopic scale, Newton's laws of physics are perfectly reversible. If you take the equations for two atoms bouncing off each other and you literally change time to negative time, the math still works perfectly. The atoms just retrace their steps. But in our macroscopic everyday reality, running things backward looks ridiculous. If you play a movie of a glass shattering in reverse, everyone laughs because it's so obviously impossible. So where on earth does this one-way reality come from if the microscopic laws don't even care about direction? To solve this paradox, we have to look at groups of particles. Section 4, order, disorder, and entropy. Picture this. Little thought experiment with me. You've got a box, and right down the middle is a barrier. On one side, you have black neon molecules. On the other, white argon molecules. This is a highly ordered state. Everything is in its right place. Now, pull that barrier out. Slowly, they start to mix. A white molecule accidentally wanders into the black side. A black molecule drifts into the white side. Pretty soon, it's just a completely mixed up, uniform gray smear. Now here is the kicker. Every single microscopic collision that happened during that mixing was perfectly reversible. But the overall mixing process, that is strictly irreversible. So the crucial point here is this concept of entropy. Entropy is our measure of disorder. But more precisely, it's the logarithm of the number of ways the insides of a system can be arranged so that from the outside, it looks exactly the same. Really let that sink in for a second. When the gases are separated, there are very few ways to arrange them. It's a highly restricted state. But once they're mixed, there are trillions upon trillions of ways those atoms can bounce around and still just look like a blurry gray cloud to us. And this is exactly why you can't unmix the gas, and why you definitely cannot unscramble an egg. Irreversibility is based entirely on perfectly reversible situations coming together to create macroscopic chaos. It's not that the laws of physics explicitly forbid the gas from unmixing. It's just that the odds of trillions of wildly chaotic, jiggling atoms accidentally wandering back into perfectly separated sides are so infinitesimally, incredibly small that it will literally never, ever happen. But hold on a second. Let's zoom out. Section 5, the cosmic arrow of time. Because this brings us to the ultimate question. If things are constantly moving from order to chaos, from separated to mixed, where did the order come from in the first place? Is the order we experience right now, the fact that we have distinct, super hot stars and cold, rocky planets, instead of just a uniform, boring, gray smear of matter, is that just some random, lucky fluctuation? Did the atoms just accidentally happen to group up and now they're busy unmixing? Or is there a deeper reason time only goes one way? The answer is honestly mind-blowing. By pointing telescopes at distant stars, astronomers have proven that the universe is definitely not just some random fluctuation. The entire universe was born in a state of extremely high order and very, very low entropy. The Big Bang wasn't just a messy explosion. It was an incredibly tightly wound, highly organized starting point. And the universe has been unwinding and increasing in entropy ever since. Literally everything we experience as the flow of time is tied to this. Growth, decay, and even human memory are just the unraveling of the universe's initial order. The only reason we remember the past and not the future is because the past was closer to that original moment of high order, and the future is inexorably sliding toward higher disorder. Our brains are quite literally just riding this cosmic gradient of entropy. Feynman reflects on this so beautifully with a specific quote. He says, "The entire universe is in a glass of wine, if we look at it closely enough. Everything is just deeply, fundamentally interconnected. The liquid, the glass itself, the light passing through it, all of it is obeying these exact same laws of thermodynamics, all of it slowly marching towards disorder, echoing the very beginning of time." And that brings us full circle, right back to our incredibly simple little gear. As the text states, the ratchet and pawl works in only one direction because it has some ultimate contact with the rest of the universe. Think about it. It only turns because we can cool it off, because the Earth naturally radiates heat out into the cold, dark vacuum of space, a vacuum created by the expanding, unwinding universe itself. If the universe wasn't actively expanding and cooling down,
that Ratchet would just heat up and fail entirely. Which leaves us with this absolutely staggering realization. Every machine we build, every action we take, every single tick of your watch is quite literally riding the wave of the Big Bang. The one-way direction of a simple mechanical gear is physically tethered to the one-way history of the cosmos. So, the next time you drop a mug or scramble an egg for breakfast, take a moment to appreciate the cosmic mechanics hiding right there in plain sight. Are you ready to see the fingerprint of the Big Bang in your everyday life? Keep your curiosity sharp, and I'll catch you in the next explainer.
Welcome to this explainer. Today, we're cracking open Chapter 47 of Richard Feynman's legendary lectures to look at the absolute magic and the rigorous physics of sound. We're going to deconstruct the wave equation, translating all that abstract math into tangible physical reality. We aren't just looking at the final equations. We're going to get our hands dirty with the elegant physical derivations that actually get us there. Let's dive in.
So here's our roadmap for this explainer. First, we'll look at the universal phenomenon of waves, then how we visualize wave propagation. After that, we'll break down the actual mechanics of sound, derive the wave equation itself, and finally, figure out what actually sets the speed of sound.
Okay, Part 1, the universal phenomenon of waves.
We see wave phenomena literally everywhere. Ocean swells, elastic waves trembling through the earth, even quantum matter waves. But sound offers this perfect, everyday mechanical playground to really grasp what a wave actually is. It completely bridges the gap between a simple swinging pendulum and these complex fields moving through space and time. But before we get bogged down in the math, we have to ask ourselves, what physical disturbance is actually happening in the invisible air molecules between my mouth and your ear right now? When an object moves really fast, like say your vocal cords vibrating, it doesn't just politely push the air out of the way. It smashes into it. It compresses it. That compression spikes the pressure, which then shoves the next layer of air, creating a traveling disturbance.
And this cascading disturbance leads to some wildly unique behaviors, like beats, which happen when two waves with slightly different frequencies interact with each other over time. Check out the two individual wave patterns at the top of this diagram, and then look at their combined effect down at the bottom. It's like a giant acoustic puzzle. When you listen to two slightly off-pitch frequencies at the exact same time, sometimes the wave crests arrive at your ear perfectly in sync, which amps up the sound. But other times, a crest crashes into a trough and they completely cancel each other out. That rhythmic rising and falling volume you hear, whoop whoop whoop, that's a beat. It's a textbook, real-world example of waves interacting over time.
Moving right along to Part 2, visualizing wave propagation.
So we've talked about time, right? But we also really need to visualize how these waves actually travel across physical space. If you look at the solid line here, that represents our wave at time 0. Now, the dashed line is that exact same shape at a later time. Let's call it t. Notice how the whole shape has just shifted over by a distance equal to its velocity, c, multiplied by that time, t. So, purely mathematically speaking, if a wave holds its exact shape while cruising along at a constant speed, we can represent it as a function of its position x minus the speed times time, f of x minus ct. That simple little expression, that's literally the mathematical fingerprint of a propagating wave.
Now here is something absolutely crucial. Sound waves don't just smash into each other and get destroyed. Thanks to the principle of superposition, they just add up and ghost right through one another. It's wild to think about, but this is exactly why you can sit in a crowded concert hall and clearly pick out the violins, the cellos, and the French horns all at the exact same time. The waves from every single instrument are coexisting in the air simultaneously, and your ear is just receiving the simple mathematical sum of all those independent, overlapping waves.
All right, Part 3, the mechanics of sound. Okay, so how do we take this high-level idea of wave propagation and ground it in the gritty physical mechanics of a gas? Let's zoom way in on the air itself. The entire physics of sound relies on this continuous three-step mechanical chain reaction. Step 1, the gas moves, which causes its density to change. Step 2, that shift in density inherently triggers a change in pressure. And Step 3, those new pressure inequalities push on the surrounding gas, which generates even more motion, and the cycle continues. But there's a really vital detail here. This whole chain reaction only acts like a wave because the distance between these pressure crests is vastly larger than the mean free path. That's just a fancy term for the tiny distance a molecule travels before it smacks into another molecule. If the sound wave was too short, the molecules would just lazily drift from high to low pressure. Everything would equalize instantly, and the wave would just fizzle out before it even started. Which brings us to part 4, deriving the wave equation.
This is where things get really fun. We're going to translate that physical chain reaction we just talked about into the mathematical language of Newton's laws. This is the real genius of physics, right? Taking physical observations and turning them into predictive math. Imagine a little invisible slab of air perfectly undisturbed on the left. But when a sound wave rips through, it displaces that air. The air at position x gets nudged a little bit, while the air just slightly further away at x plus delta x gets nudged a slightly different amount. Because the front and back of this slab are moving by different amounts, the total volume of that slab actually changes. And if you force the exact same amount of matter to suddenly take up a larger or smaller volume, well, its density absolutely has to change.
So we can write out that first step pretty simply. The change in density, what physicists call the excess density, is directly tied to how much the air is being stretched out. If the displacement gets bigger as you move along the x-axis, the air is basically being pulled apart. And when you stretch it out, obviously, the density drops. That is exactly why there's a negative sign in this relationship. More stretch literally equals less density.
Now for step 2. Those density changes instantly create pressure differences. If you look at the arrows pressing in on our tiny slab of air here, you'll see it has a certain pressure pushing on it from the left side, and a slightly different pressure pushing back from the right side. Because these two opposing pressures aren't perfectly balanced, you end up with a net force pushing on this little slice of air. And here is the absolutely crucial payoff. This is literally just Newton's second law of motion applied to a tiny pocket of air. Good old F equals ma. Force equals mass times acceleration. The mass of our little air slab, multiplied by how fast it's accelerating, which in calculus terms is the second derivative of its displacement over time, must perfectly balance out the net force created by that uneven pressure we just looked at. So, by mashing these physical steps together and canceling out the extra variables, we arrive at it, the universal wave equation. This is just a beautiful piece of logic. We took the equation for density changes, plugged it into the equation for pressure changes, and dropped the whole shebang right into Newton's law of motion. And what magically falls out is this incredibly elegant equation mathematically proving that a mechanical disturbance will propagate at a constant speed. It shows that the second derivative with respect to space is directly proportional to the second derivative with respect to time. And the magical constant linking them together? Simply 1 over the wave speed squared.
And that leads us perfectly into part 5, the speed of sound.
So, what exactly determines that constant speed limit of sound traveling through the air? Well, it turns out even absolute geniuses get it wrong sometimes. When Sir Isaac Newton first tried to calculate the speed of sound, he assumed that when air gets compressed, the heat generated by that compression immediately conducts away, keeping the temperature perfectly constant. He assumed it was an isothermal process. But his math just didn't match the real-world measurements. It took years before a mathematician named Laplace came along and figured out the reality. Laplace realized that the compressions and rarefactions in a sound wave happen so unbelievably fast, and the distances are so enormous compared to a tiny molecule's path, that there's literally no time for the heat to escape. The air physically heats up when it's squished and cools down when it's stretched. By accounting for this adiabatic process, Laplace's math perfectly predicted the actual speed of sound.
And all of this leads to this really beautiful revelation from Feynman's lectures. Sound isn't magic. Its speed is entirely physically constrained by how fast the gas molecules themselves are already zipping around and bumping into each other in the air. Think about it. Since a sound wave is literally propagated by molecules crashing into their next-door neighbors, the wave obviously can't travel any faster than the molecules themselves are moving. The math elegantly proves that the speed of sound is, as Feynman put it, roughly somewhat less than the average speed of the molecules. It's just an incredible concept that perfectly connects the microscopic chaos of bouncing gas particles to the smooth, macroscopic order of a sound wave.
As we wrap up this explainer, I want you to consider something kind of mind-blowing. If this exact same mathematical logic, the wave equation, maps the physical, chaotic bumping of air molecules to the behavior of light traveling through a vacuum, and even to the probability amplitudes of quantum particles, what other invisible secrets is the universe still hiding from us? The wave equation isn't just a quirky rule about sound, it is a fundamental language of nature itself. So the next time you're sitting in a symphony, or honestly, even just listening to the sound of your own voice, take a second to appreciate the invisible mathematical chain reaction of mass, pressure, and acceleration that is making it all possible. Keep questioning, keep learning, and thanks so much for exploring this with us today.
Hey everyone, and welcome to The Explainer. Today, we're going to trace one single, absolutely incredible underlying principle of physics. We're taking it all the way from the tangible reality of the sounds we hear every single day, right down to the fundamental mind-bending nature of matter itself. And that principle? It's the physics of overlapping waves, specifically a super cool phenomenon known as beats.
Okay, let's dive into this. On our agenda today, the phenomenon of beats, visualizing wave interference, radio waves and sidebands, phase versus group velocity, and finally, quantum waves and particles. Section 1. The phenomenon of beats, the acoustic reality. So, if you've ever listened to two instruments tuning up, or maybe the twin engines on an airplane, you've probably heard this pulsing wah, wah, wah sound. That right there is the real-world acoustic reality of two slightly different frequencies overlapping in the exact same space. Imagine the two distinct waves at the top are sound waves from two tuning forks. Because their frequencies are just slightly different, their mathematical relationship to each other is constantly changing. When the crests of the two top waves coincide, they actually add up to a strong, amplified wave. But as time goes on, the faster wave pulls ahead of the slower one. Soon enough, the crest of one aligns with the trough of the other, and they practically cancel each other out, dropping the sound almost to zero. This creates that sweeping, pulsing dotted envelope you see outlining the bottom wave. So the crucial point here is that a beat is simply a slowly pulsating intensity caused by the interference of two wave sources with slightly different frequencies. When you mathematically add two nearby frequencies together, the result is an average frequency that pulses in strength exactly at the mathematical difference between the two original frequencies. It's actually pretty simple. If one wave is 100 cycles per second and the other is 102, you are going to hear a pulsing beat exactly twice per second. Section 2. Visualizing wave interference, the geometry of interference. To really wrap our heads around the physical meaning of these adding waves, let's step away from the squiggly lines for a second and look at rotating vectors. We can represent these individual waves as two vectors, or basically arrows, spinning in a circle, kind of like the hands of a clock. The length of the arrow, A1 or A2, represents the wave's amplitude, and the speed it spins represents its frequency. Now, if the frequencies were exactly equal, these two clock hands would spin together locked in a fixed shape, giving us a steady, unvarying sum. But because the frequencies were slightly different, they go around this circle at slightly different speeds. Let's move on and see how this builds. Imagine riding along with one of those vectors. Let's freeze it, pointing straight to the right at position 1. Because the second vector is spinning at a slightly different speed, from our perspective, it slowly drifts away. It opens up through positions 2, 3, and 4, all the way to position 5, where it's exactly 180 degrees opposite. At that exact moment, the vectors actually subtract from each other, and the resulting wave is incredibly weak. Then it continues to sweep around, back to position 9, where they line up perfectly again, creating a really strong wave. This opening and closing geometry is the exact physical mechanism behind the pulsing amplitude we hear as an acoustic beat. Section 3. Radio waves and sidebands, broadcasting information. So far, we've only talked about sound. But what happens if we shift the scale to the high-frequency electromagnetic waves zooming through the air all around us right now? That brings up a super practical question. How does this simple wave math actually let you listen to the radio? Well, the answer is amplitude modulation, or AM. Think about an AM radio station. It generates a steady, incredibly fast, high-frequency oscillation, say 800,000 cycles a second. This is known as the carrier wave. When a singer sings into a microphone at the station, the equipment modulates or changes the amplitude of that super fast carrier wave so its outer envelope perfectly matches the relatively slow audio vibrations of the singer's voice. Your car radio receiver then strips away the fast carrier wave, reads that pulsing envelope, and plays the singer's voice right back to you. But here's where the math of beats reveals something totally profound. When you pulse a wave's amplitude like that, you are mathematically adding waves together in superposition. Creating that envelope actually generates brand new frequencies. You have the original carrier frequency right in the middle, but you also generate two sidebands, one at the carrier plus the audio frequency, and one at the carrier minus the audio frequency. The actual information, the singer's voice, literally lives in those sidebands. These sidebands are mathematically identical to the acoustic beats we just talked about. And this is a hard physical reality, not just some neat math trick. It dictates the entire structure of modern telecommunications.
Because a human voice spreads up to roughly 10,000 cycles per second, an AM radio station nominally broadcasting at 800 kilocycles actually takes up physical frequency space, all the way from 790 to 810 kilocycles. If stations aren't kept separated on the radio dial, their sidebands will overlap and create pure chaotic noise, which is definitely not what you want to hear in your morning commute. It's also exactly why complex signals like television broadcasts require massive 6 megacycle wide bands just to fit all their high-frequency visual sideband information.
Section 4. Phase versus group velocity. Moving modulations. Now, what's really interesting about this next slide is how it introduces a fascinating physical complication. What happens when these waves aren't just oscillating in time, but are physically moving forward through space at varying speeds, like light traveling through a dense material such as glass or carbon? Well, this physical reality forces us to split our idea of speed into two completely distinct concepts. When you add moving waves of slightly different frequencies together, the underlying ripples, the nodes of the wave itself, travel at what we call the phase velocity. But the beats, that pulsing envelope or modulation we created by adding them together, travels at its own distinct speed, called the group velocity.
This distinction beautifully resolves one of the great apparent paradoxes in physics. You see, the phase velocity of X-rays moving through a block of carbon is actually faster than the speed of light in a vacuum. But wait, Einstein tells us nothing can carry signals faster than light, right? Well, the resolution is actually quite simple. The group velocity is what carries the actual signal, the physical information, the modulation. And the mathematics of overlapping waves guarantee that the group velocity in this scenario is always slower than the speed of light. So the underlying microscopic ripples might race ahead, but the envelope carrying the real-world information always mathematically obeys the cosmic speed limit.
Section 5. Quantum waves and particles, the quantum leap. We are now going to take the exact same mathematical principles of overlapping wave beats we saw in acoustic tuning forks and apply them directly to the fundamental nature of matter itself. In quantum mechanics, a particle, like an electron, is described by a wave of probability. But an electron isn't smeared evenly across the entire universe. It's usually localized in one specific place. Notice that pulsing lump? By carefully adding together multiple quantum waves with slightly different frequencies, they interfere and cancel each other out, everywhere except in one pulsing lump. This is a localized wave train, and it's remarkably similar to a radio envelope. The center of this lump is where the particle is most likely to be found. And this brings us to an absolutely profound conclusion. The original source text notes, the quantum theory will go into the correct classical theory only if the group velocity is equal to the velocity that we would obtain classically for a particle. Let that sink in for a second. What this physically means is that as this wave packet moves through space, the speed of the lump, the modulation, the beat, represents the actual physical movement of the quantum particle itself. The velocity of the classical particle precisely equals the group velocity of the quantum wave. V equals Vg. It's just a stunning realization. The exact same mathematical interference that governs how an AM radio station broadcasts its sidebands beautifully ties the abstract, probabilistic waves of quantum mechanics directly to the classical momentum of a moving particle. Which leaves us with this final provocative thought. How is the entire universe, from a singer's voice vibrating in the air to a moving electron racing through space, connected by the simple math of overlapping waves? Today, we've traced one single concept, the interference of slightly different frequencies from the wah-wah beats of sound to radio dials, past the speed of light paradox, and straight into the very heart of a quantum particle. It is a breathtaking reminder of the magnificent, unified structure of physics. Thank you so much for joining me on this explainer. I passionately encourage you to keep exploring, keep questioning, and keep discovering the hidden physical connections in our universe. Welcome to this explainer. Today, we're going to explore how this simple pluck of a string unlocks some of the absolute most profound secrets of quantum mechanics. It sounds like a massive leap, right? Going from a vibrating piece of twine all the way to the very building blocks of matter. But as we'll see, physics has a beautiful habit of repeating its best tricks. Here's the roadmap for our explainer today. We'll hit the secrets of confined waves, discovering natural frequencies, moving to two dimensions, modes and mechanical systems, the grand linear principle, and finally, the quantum mechanics connection. Let's get right into it. Part 1, Secrets of Confined Waves. So, what actually happens when a wave hits a wall? Imagine a simple, one-dimensional wave. Picture a long string tied super securely to a totally solid brick wall.
If you send a wave, like a little bump, down that string, it has to do something when it hits that immovable boundary, right? The math here is incredibly cool. You can imagine that the incoming wave actually cancels out with a hypothetical reversed wave coming from the other side of the wall. Because the wall literally cannot move, these two waves, the real one and the imaginary upside-down one, meet and perfectly cancel each other out right at the boundary. The result? The wave reflects back entirely upside down.
Now, when we trap these waves and get them bouncing back and forth perfectly smoothly, we run into a foundational concept in physics called a mode. Think of a mode as a specific pattern of motion. In this pattern, every single point in the system moves perfectly in time, specifically like a smooth sine wave, at the exact same frequency. Sure, some parts of the string might move a lot, and some parts, which we call nodes, might not move at all, but the overall spatial pattern, it stays completely fixed. It's just a highly synchronized, beautiful dance. Moving on to part 2, discovering natural frequencies. This is all about fitting the wave to the string. If you tie a string down at both ends, like a guitar string, it can't just vibrate any old way it wants to. For the string to vibrate smoothly without instantly canceling itself out, the wave has to neatly fit into the string's length. The lowest energy shape is just a simple, single arc. The next step up has a stationary node right in the center, giving it an S shape. Go up one more and you get 2 nodes. Because the ends are clamped down tight, the string can literally only move at these specific natural frequencies where the wave fits perfectly. Here's the really crucial takeaway. In one dimension, these natural frequencies stack up as perfect, incredibly clean multiples. If the lowest frequency, that very first mode, is, say, 100 oscillations a second, the second mode will be exactly 200. The next, exactly 300. It forms this beautiful harmonic sequence of whole numbers, 1, 2, 3, and so on. Honestly, this simple mathematical perfection is exactly why string instruments sound so pleasing to our ears. All right, part 3, moving to 2 dimensions. We're about to break that simple multiples rule. Let's step out of flat 1D for a second. Consider a 2-dimensional surface, maybe a rectangular rubber drumhead that's pinned down tight on all 4 edges. If you strike it, waves ripple outwards and bounce off all the sides. To find the modes here, the math gets significantly more complex, because the wave has to perfectly reflect and cancel out along both the x and the y boundaries at the same time to keep those edges perfectly still. And this brings us to a really surprising twist. Unlike our simple guitar string, natural frequencies in 2 or more dimensions are almost never simple harmonic multiples. No way! If you calculate the modes for that rectangular drumhead, you get messy decimal ratios. It might jump from a baseline frequency of 1 up to 1.12, then 1.41, then 1.8. The simple integer pattern is just completely gone. Believe it or not, we actually experience this multidimensional complexity every single day. Just think about your own mouth. It's a complex 3D resonator with incredibly varied non-harmonic frequencies. When you speak, your vocal cords create a tone, but your mouth cavity actually shapes it. So why does sucking in helium make you sound like a cartoon character? Well, helium is way less dense than air, meaning sound waves travel much faster through it. This increase in wave speed instantly raises all the resonant frequencies inside the complex cavity of your mouth. Your vocal cords are vibrating at the exact same speed they were before, but the modes of your mouth have shifted way up, completely and hilariously altering your voice. Section 4, Modes in Mechanical Systems. Let's apply these waves to solid objects. We don't just see modes in continuous systems like strings or drumheads. Think about a simple mechanical system, like 2 pendulums swinging side by side, connected by a spring. Because there are only 2 movable objects here, physicists say the system has 2 degrees of freedom. And just like our string tied to the wall, this pendulum system has its own specific, perfectly synchronized modes. Since it has 2 variables, it has exactly 2 modes. The first mode is when the pendulums swing perfectly together, totally parallel. In this scenario, the spring never stretches or compresses at all. It's literally as if the spring isn't even there, and they just swing steadily at their normal base frequency. Now, the second mode is when they swing exactly opposite to each other. When they move apart, the spring stretches and violently pulls them back in. When they move together, it compresses and shoves them apart. This extra dynamic force from the spring speeds up the oscillation, giving us a second, much higher natural frequency. Which brings us to part 5. The grand linear principle. We're going to combine these simple motions. When you actually pluck a guitar string in the real world, you aren't just triggering one perfect, simple mode. You're actually triggering a whole bunch of them at once.
If we take our first mode, that single arc, and overlap it with our second mode, the S shape, at the exact same time, their distinct waves just add together. The result? It creates this really complex traveling bump that bounces back and forth across the string. And this leads us to a massively important rule for linear systems in physics. Think about that chaotic traveling bump bouncing across the string from a second ago. It looks super complex, maybe even unpredictable. But according to this principle, no matter how complicated or chaotic a motion seems, it can always be broken down into a simple combination of its fundamental modes. Every complex movement is basically just a recipe. A pinch of mode 1, a dash of mode 2, and maybe a cup of mode 3. It's an absolutely incredibly powerful way to decode the universe.
Finally, part 6, the quantum mechanics connection. We're going from strings all the way to atoms. Okay, you might be sitting there wondering, what on earth does the mechanics of a bouncing rubber band or a swinging pendulum have to do with the fundamental building blocks of matter? It's a fair question, but here's the secret. The math behind waves doesn't care what the wave is actually made of. In the weird world of quantum mechanics, an electron trapped inside an atom isn't just some tiny billiard ball. It acts like a confined wave, specifically a wave of probability, a wave that literally tells us where the electron is most likely to be found. And just like that string perfectly confined between two solid walls, the electron wave is confined by the atom. Now, here is where the magical translation happens. In classical physics, confined waves must have definite natural frequencies. While in quantum mechanics, frequency is directly equivalent to energy. Therefore, these confined quantum waves can only exist at definite, distinct energy levels. So, as we wrap up this explainer, I want you to consider this. The reason an atom has specific energy levels, and frankly, the reason chemistry works the way it does, is fundamentally the exact same reason a guitar string plays a specific note. The very atoms that make up the solid matter of your body are governed by the exact same physical rules as a plucked string. You are, quite literally, a complex symphony of confined probability waves, singing a silent quantum song. And if the very atoms of your body are just confined waves singing specific quantum chords, well, what other hidden frequencies in the universe are just waiting for us to discover them?
Welcome to the explainer. Today we're going to do something really cool. We are going to completely demystify the hidden, almost incredibly beautiful math behind sound. Seriously, we're going to trace this awesome thread of logic from something as simple as a plucked string all the way to modern high-powered lasers. And along the way, we'll see how literally everything relies on waveforms.
To get us started on our main theme today, which is basically that art is secretly just math, let's look at a pretty mind-blowing realization from the ancient Greek philosopher Pythagoras. He figured out that beautiful music, specifically those really pleasant-sounding chords we all hear and love, well, they're essentially just simple fractions. He actually believed this hinted at some massive, deep cosmic order. They even called it the music of the spheres.
So here's our roadmap for the explainer today. First step, music, math, and Pythagoras. Second, the anatomy of a tone. Third, Fourier's mathematical recipe. Fourth, when the rules break. And finally, number 5, tech built on distortion.
Okay, jumping right into Section 1, Music and Pythagoras, the first discovery.
So Pythagoras noticed something that totally shocked the ancient world. He observed that if you have strings with lengths and exact ratios of 2 to 3, they produce this incredibly pleasant musical chord, a fifth to be specific. Now, why was this such a huge deal? Because it was literally the very first numerical relationship discovered in nature completely outside of geometry. Think about that. It proved that a simple physical measurement of length could predict a totally subjective human experience, like hearing a pleasant sound. It really showed that arithmetic could be the ultimate tool for decoding nature.
Moving on to Section 2, the anatomy of a tone. Let's look at what sound physically is.
To take this from pure philosophy into physical reality, we really need to compare two things. Imagine a stamped foot. That produces an irregular, totally random vibration on your eardrum. Basically, it's just noise. But compare that to a musical note. A musical tone relies completely on a repeating pattern of pressure. It's that periodicity, that specific, uneven shape repeating itself over and over and over again that our brains magically interpret as music.
You can actually see this perfectly right here. Notice the chaotic, jagged scribbles of noise? Now contrast that with the perfectly repeating periodic pattern of a musical tone right below it. Both of these are going to make your eardrum vibrate, but only that repeating pattern is actually going to sing to you.
Now, when musicians and physicists talk about a tone, they're really measuring three main characteristics. First, our brains process the magnitude, or the actual height of these waves, as loudness. Second, we process the length of the period, which is just how fast the wave repeats, as pitch. And third, the specific internal shape of that repeating wave, that dictates what we call the quality of the tone.
All right, let's get into Section 3, Fourier's mathematical recipe, where we start deconstructing these waves.
Check this out. See how that messy, complex wave at the top is actually just a stacked combination of the really simple, pure harmonic sine and cosine waves lined up below it? This visually proves an incredible theory by the mathematician Jean-Baptiste Joseph Fourier. He figured out that if you just add up the simple waves, you can perfectly recreate the complex one. It's an absolute game changer.
We call this whole process Fourier analysis. The best way to think about it is like, well, imagine the complex wave is a fully baked cake. Fourier analysis is the mathematical procedure we use to reverse engineer the exact recipe of simple ingredients, those simple harmonic components that originally baked it. Literally every periodic sound you've ever heard in your entire life can be broken down into these basic mathematical ingredients.
But how do we actually find those ingredients without getting completely buried in intense calculus? Well, Fourier used this brilliant mathematical sieve. It's a clever little three-step trick. First, you multiply the complex wave's equation by a specific target harmonic. Second, you just average that result out over time. And because of how the math of sines and cosines works, step 3 honestly feels like pure magic. All the non-matching terms just mathematically drop to zero. Boom, gone. The absolute only thing left standing is the exact amount of the specific harmonic ingredient you were searching for.
And the crazy thing is, this math works flawlessly, even on really bizarre jagged shapes. Take a look at this rigid square wave. It violently jumps from +1 to -1. But using Fourier's math, it deconstructs neatly into an infinite series of oddly proportioned harmonics. To get specific, it uses only the odd harmonics, like the first, third, fifth, and so on, and their amplitudes get smaller in exact inverse proportion to their frequencies.
So, circling back to what we said earlier, that elusive characteristic we called quality is truly just the harmonic recipe. That exact recipe is why your friend's voice saying "ee" sounds fundamentally different from them saying "ah." You change the mouth shape, you literally change the frequency recipe. It's the exact same reason an oboe doesn't sound anything like a violin, even if they're playing the exact same pitch.
Okay, Section 4, when the rules break. Let's talk about nonlinear responses. Because, right when we fully wrap our heads around this perfect linear math, we have to throw a wrench into the whole system. Take a look at the difference here between a perfectly proportional linear system, like say a nicely tuned piano string, and a curved, nonlinear response that physically warps our wave. If you force a pure tone into a nonlinear system, the output wave isn't a pure cosine function anymore. It gets physically warped. You can see it becomes noticeably peaked at the very top and flattened out at the bottom.
Now, this nonlinear distortion absolutely breaks our original pure wave, but astonishingly, it gives birth to three brand new phenomena. First is rectification, which actually forces the entire wave to shift its average value. Second is the birth of brand new, higher harmonics that literally weren't even there to begin with. And third is frequency modulation, which essentially mashes different frequencies together to create entirely new outputs.
Which brings us to our final part, Section 5, Tech Built on Distortion, and how all this builds modern tech.
Because believe it or not, this mathematical messiness, it's exactly what builds our modern world. Take radio and audio, for example. Good old AM radio completely relies on this nonlinear modulation. It deliberately uses those exact messy distortion effects to combine your low-frequency voice with a high-frequency carrier signal so it can broadcast across the globe. On the flip side, super expensive hi-fi audio equipment desperately tries to remain perfectly linear. Why? Because any nonlinear response in a speaker is going to generate unnatural harmonic destruction that completely ruins the natural sound of the music.
But hold on, because this nonlinear math actually escapes sound entirely and applies to light too. When scientists push an intensely strong red laser beam through a piece of glass, the light interacts non-linearly with the material. And get this, it physically generates the second harmonic of that light wave. Because the frequency is doubled, a pure red beam goes in and actual blue light comes out. We literally use the physics of distorted sound to transform the color of lasers. How wild is that?
Which leaves us with a pretty fascinating final thought. It's widely believed by physicists that human hearing itself is surprisingly nonlinear,
Yeah, our own ears and brains are constantly producing fake harmonics and difference frequencies inside our heads that aren't even physically present in the air around us. So, considering all of this, we really have to ask a profound question. When we sit back and listen to a beautifully composed song, are we actually feeling the music, or are our brains just doing the arithmetic? Definitely think about that the next time you put on your favorite album.
Welcome to this explainer. Today, we're diving straight into the complex and totally fascinating physical phenomena of waves, drawing directly from Chapter 51 of Richard Feynman's iconic lectures on physics. We often think of waves as just simple, predictable ripples. But when we actually look closely at the physics, we uncover a world of incredible complexity. So we're going to take a structured journey today to unpack the deep physical meanings behind how waves actually work. Here is our roadmap for this explainer. 1. Bow waves. 2. Shock waves. 3. Earthquakes. And 4. Surface waves. Let's jump right in. Section 1. Bow waves breaking the barrier. Take a look at how a bow wave actually forms. Imagine a sound source zooming from left to right. At any given split second, it generates a sound wave that expands outward in a circle. But because the source itself is traveling faster than the speed of sound, it's literally outracing its own expanding wave. By the time it releases the next wave, it's already way further ahead. These overlapping, expanding circles left behind geometrically line up to form a perfect tangent line, creating a 3D cone-shaped wake. And that cone right there? That's your bow wave. Now here's where it gets wild. This phenomenon isn't just limited to sound in the air or a boat on a lake. It actually happens with light, too. I know, you're probably thinking, wait, nothing moves faster than light. Well, true, in a vacuum, but in a medium, like glass or water, light actually hits the brakes. So if a high-energy charged particle is shot through glass faster than the speed of light in that specific glass, it produces a visible, glowing, conical wake. It's called Cherenkov radiation. It's exactly the same physics as a sonic boom, just played out with light. Figuring this out literally won the Nobel Prize back in 1958. Moving on to Section 2. Shock waves, the pileup. Okay, track this pressure wave over time with me. If you look at the contour from left to right, you can see the back of the wave, that higher pressure region, is literally catching up to the front as time moves forward. It just keeps closing the gap until it overtakes it, creating this incredibly steep edge. But why exactly does the back travel faster than the front? Well, it all comes down to a physical pileup effect. When a wavefront blasts through the air, it compresses the gas super fast. This is an adiabatic compression, meaning the heat has zero time to escape, so it instantly heats the air right behind the front. And here is the kicker. The speed of sound is actually faster in hotter air. So the air at the back of the wave is surfing through a hotter medium than the air at the very front. Those rear disturbances literally ride faster, catch up, and just pile up at the leading edge. Think of it like snow piling up on the blade of a speeding snowplow. That heat-driven pileup creates that sharp, explosive wall we experience as a shock wave. Section 3. Earthquakes. Waves in solids. Unlike fluids like air or water, solid objects do something completely unique. They carry two totally different kinds of waves. First up, we have compressional, or longitudinal waves. Think of these like sound in a gas, just straight up pushes and pulls. But solids also carry transverse or shear waves. See, a solid really doesn't want to be distorted, so if you shove it sideways, it tries to pull itself back. It wobbles and recoils exactly like you just pushed a block of jello. When an earthquake hits, it unleashes both of these wave types deep into the Earth. And since the Earth's liquid core simply can't carry those transverse shear waves, seismologists can literally use the arrival times of the waves that do make it to virtually map out the hidden architecture inside our planet. And that brings us to one of the most mind-blowing measurements in all of seismology. After the massive 1960 earthquake in Chile, the entire Earth literally rang like a giant bell for days. Seismologists mapped the planet's natural resonant frequencies, which you're seeing in the broad spectrum on the left. But if you look really closely at the high-res data on the right, they found a totally mysterious spectral doublet, basically a split in the Earth's lowest vibration mode, showing peaks at 54.7 and 53.1 minutes. So why two peaks instead of just one? Well, it's highly likely caused by the Coriolis forces from the Earth spinning. Waves traveling with the Earth's rotation move at a slightly different speed than the ones going against it, which literally splits that fundamental tone right in two. How cool is that? Okay, let's surface for Section 4. Surface waves, deceptive water. We all see ocean waves constantly rolling onto the beach. But let's pause and think about the physics here for a second. Are water waves longitudinal compressions, like sound? Or are they transverse, shear waves, like a plucked guitar string? Well, surprise, they're actually neither. Because water is essentially incompressible, the molecules can't just bunch up together, and they can't simply move straight up and down either, because the water has to go somewhere. So what happens is the molecules actually move in circular orbits. It's this beautiful, complex mix of both longitudinal and transverse motions working perfectly together. And as you dive deeper beneath the surface, those circles just get smaller and smaller until the motion practically disappears altogether.
But wait, water gets even more complicated. We actually have to distinguish between two completely different speeds here, phase velocity and group velocity. Phase velocity is the speed of an individual wave crest, while group velocity is the overall speed of the entire bunch or packet of waves. If you ever watch the wake behind a moving boat, you'll see this fascinating optical illusion. The individual wave crests move forward through the group at the phase velocity, but then they just die out as they hit the front, while brand new ones mysteriously form at the back. So the overall group of waves is actually only moving at exactly half the speed of the individual crests inside it. Mind-bending, right?
And this perfectly captures just how incredibly complex water waves really are. Get this, how fast a wave moves depends entirely on its wavelength. Tracking this curve from right to left, on the right side, we have long gravity waves. The longer they are, the faster they go. Simple enough. But as the wavelength shrinks and we move left along the curve, the speed actually drops to a minimum. Then, something totally weird happens. When the wavelengths get incredibly tiny, gravity isn't the boss anymore. Surface tension takes over. We call these capillary ripples. And for these little guys, the shorter they are, the faster they travel. Because of this bizarre quirk in the physics, if you make a sharp, sudden disturbance in the water, those super fine capillary ripples will actually speed right out and run ahead of the main wave. It really completely reframes the everyday stuff as deeply, deeply complex. From the shockwave of a supersonic jet piling up in heated air to our entire planet ringing like a split bell after an earthquake, to just the simple wake of a boat hiding competing phase and group velocities in plain sight, it leaves us with a pretty fascinating question to chew on. The next time you're just looking at a simple stream flowing past a rock, what entirely new physics-adjusted forces are you going to notice? Thanks so much for joining me for this explainer. Keep observing and keep questioning.
All right, welcome to this explainer. Today we're going to dive right into one of the most absolutely fascinating paradigm shifts in all of physics. We're talking about the incredible realization that the universe's rules of symmetry are, well, brilliantly imperfect. You know, we usually think of symmetry as a visual thing, right? Like a perfect sphere, a snowflake, or a reflection in a mirror. But in physics, symmetry is actually about the underlying laws of reality itself. And as we're about to see, the universe loves symmetry right up until the exact moment it spectacularly decides to break its own rules.
Here is a quick look at our agenda for today. First, the rules of symmetry. Then, mirrors and molecules. 3, vectors and magnet mirrors. 4, calling a Martian. 5, the fall of parity. And finally, antimatter and broken perfection. Let's get to it.
Section 1. The rules of symmetry. To kick things off, we really need to establish what physicists actually mean when they say the universe loves symmetry. It's definitely not just about things looking pretty. It's a rigorous mathematical foundation of reality. The crucial point here is that a physical law is symmetrical if an operation, like, say, moving an experiment in space or time, doesn't change the outcome at all. Think about it like this. If I build a clock in New York and then build the exact same clock over in London, the laws of physics dictating how those gears turn remain perfectly identical. That's what we call translation in space. And if I start the clock on Tuesday or wait and start it on Thursday, it still takes exactly the same. That's translation in time.
But, you know, not everything is symmetrical. You can't just change whatever you want and expect physics to play along. Imagine a tiny, beautiful model cathedral made entirely out of matchsticks. It holds together perfectly on your desk. But what if you took that exact same design and scaled that matchstick cathedral up to the size of a real stone cathedral? Well, it would instantly collapse under its own weight. Why? Because the volume, and therefore the weight, grows way faster than the cross-sectional strength of the materials. Gravity and material strength just do not scale symmetrically. The fundamental laws of nature actually have a definite, absolute scale baked right into them.
Now, this is where it gets really staggering. Quantum mechanics links these geometric rules of symmetry directly to the profound conservation laws of the universe. This is a huge realization. The fact that physical laws don't change when you move through space, that directly dictates the conservation of momentum. The fact that laws don't change as time passes, that is the exact reason energy is conserved. Literally, for every continuous symmetry in the physical world, there is a corresponding conservation law governing it. It's like a beautifully connected puzzle.
Moving right along to Section 2, Mirrors and Molecules. Let's see how nature handles the ultimate symmetry test, looking in a mirror. Does the universe actually care about right versus left? If you look closely at biology, you might actually think it does. Take the amino acid alanine, for example. It's a fundamental building block of proteins. In literally every living creature on Earth, alanine is left-handed in its molecular structure, what scientists call L-alanine. But here's the catch. If you synthesize alanine in a lab from raw gases, you get a perfect 50-50 mix of left-handed and right-handed molecules. Fundamentally, physical and chemical laws insist that both left and right-handed molecules should behave identically. Biology's total preference for left-handedness, that's just a historical accident, a slightly lopsided starting point billions of years ago that just kept copying itself. So, basic physics doesn't seem to favor left over right at all.
All right, Section 3, Vectors and Magnet Mirrors. To dig a little deeper into this mirror symmetry, we have to look at how different types of forces and the mathematical arrows we use to describe them act when they're reflected. We're testing whether a perfectly mirrored universe would run exactly like ours does.
Take a look at this ordinary polar vector. It's just a straight step in space. If you take a step toward a mirror, your reflection steps right back toward you. The vector arrow simply changes its head, just as the whole space turns inside out. It's a very straightforward, what we'd call an honest reflection. But watch what happens when we introduce rotations. Look at this spinning wheel. If it spins clockwise, the mirror image spins in a way that perfectly matches the physical motion. But the mathematical arrow we use to describe that spin, which is called an axial vector, doesn't flip the same way a standard spatial step does. It's an artificial mathematical construct, and it behaves completely differently in the mirror world. And this brilliantly illustrates how the physical laws of our universe adapt to the mirror to deal with that weird rotation math. Because magnetism is fundamentally just the axial vector of spinning charges, nature physically flips the poles in the mirror world to keep everything operating with perfect mathematical symmetry. When you look at a magnet in a mirror, the current's reflection actually forces the magnet's north pole to swap and become a south pole. Nature just quietly flips it so the whole shebang continues to operate with perfect symmetry. Which brings us to Section 4, Calling a Martian. Okay, so physics protects symmetry by flipping poles in the mirror. If you do an experiment with a magnet and your mirror twin does the mirrored experiment, the results are going to perfectly mirror each other. But this leads us to a really incredible, mind-bending thought experiment.
Imagine we finally established contact with a Martian, but we can only talk to them over the radio. We can't send them any physical objects at all. We describe our height in atoms, our basic shape, our organs. We tell them we have a heart. They ask, okay, where does the heart go? We say, on the left side. And the Martian pauses and asks, what exactly is left? Is there any physical experiment we can tell the Martian to perform that will definitively give them the absolute, universal concept of left?
And that thought experiment perfectly sets up Section 5, the fall of parity. For a very long time, the answer in physics to that Martian question was a flat no. Because the universe was thought to be perfectly symmetrical, left and right were just considered arbitrary human conventions. But then, physicists discovered a massive plot twist in the subatomic world.
Here is the smoking gun that changed physics forever. Researchers were studying these tiny subatomic particles called tau and theta mesons. They had the exact same mass, the exact same lifespan. They were clearly the exact same particle. Yet, inexplicably, one broke into 3 pieces, which is an odd parity state, and the other broke into 2 pieces, an even parity state. Now, according to the strict rules of quantum reflection symmetry, which is known as the conservation of parity, a single particle cannot decay into both states. It meant the golden mirror rule was fundamentally broken.
To see if this symmetry was really, truly broken, a physicist named Chien-Shiung Wu designed an absolutely brilliant test. She took cobalt-60 atoms, cooled them down to near absolute zero so they'd stop jiggling around, and used a really strong magnetic field to line up all their north and south poles. As the cobalt-60 decayed, it shot out electrons. If the universe was truly symmetrical, those electrons should shoot out evenly in all directions. But they didn't. They heavily preferred shooting downwards, away from the South Pole. The action was fundamentally unsymmetrical.
This was the massive aha moment that just shocked physicists worldwide. As Richard Feynman put it, the magnet has grown hairs. The south pole of a magnet physically pushes these weak decay electrons away. It acts completely differently than the north pole. And you know what this means? It means we finally have a way to define left and right to our Martian. We just tell the Martian over the radio to build Miss Wu's cobalt-60 experiment. The direction the electrons shoot out gives them an absolute physical definition of right and left, with zero mere trickery involved.
Bringing us to our final part, Section 6, Antimatter and Broken Perfection. So if the unbreakable rule of left-right symmetry is fundamentally broken at the subatomic level, how does the universe fix it? Because nature doesn't usually like to leave loose ends.
Well, the universe restores balance by combining rules. Physicists realize that if you swap right for left, you must also swap matter for antimatter. A right-handed clock made of normal matter does not behave like a left-handed clock made of normal matter. But if you build that left-handed clock out of antimatter, it runs perfectly. True symmetry requires reflecting both space and charge at the exact same time. The universe is perfectly symmetrical, but only if you swap left for right and matter for antimatter simultaneously.
Which brings us right back to our Martian friend. Because of this combined fix, say we give the Martian our instructions. He builds the cobalt-60 experiment, but if his solar system happens to be made of antimatter, his experiment will run completely in reverse. He'll define left totally backward. So if we finally build spaceships, meet halfway in space, and the Martian reaches out to shake our hand with his left hand, watch out. His anatomy is reversed because he is made of antimatter, and shaking his hand would cause a massive, catastrophic annihilation.
This whole journey leaves us with a truly profound mystery. For almost everything we see, gravity, electricity, big everyday objects, the universe is perfectly symmetrical. But in this one tiny, weak subatomic interaction, it's just a little bit lopsided. Why is nature so nearly symmetrical, but not completely? Just like the beautifully carved Japanese gate at Nikko, which features one intentionally upside-down pillar in an otherwise absolutely flawless design, we are left wondering, did the universe build its physical laws nearly symmetrically, leaving just one tiny flaw so we wouldn't be jealous of its absolute perfection? It's a question that still keeps physicists up at night, and hopefully it gives you something fascinating to think about too. Thanks for joining me for this explainer.